Hey guys, good evening, and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Quickly let me know in the chats with some fire emojis, everyone in the chats. Good evening people, good evening and welcome back. Good evening and welcome back. Good evening and welcome back. So quickly in the chats, if all of you can hear me, if I'm perfectly audible, visible to everyone. Quickly let me know in the chats, people. Yeah, so that we can start the session directly. Let me know in the chats quick. Welcome people, welcome back, welcome back. All right, so my dear students, as you all must be knowing, today we are going to have one mega marathon of your complete class 11th physical chemistry, right? And one thing I'm telling you for sure, if you are going to follow this particular session till the end, my dear students, for sure, you guys are going to secure some 60 to 70 marks perfectly. Yeah, because you know every single thing I'll be starting from the basics, from the scratch. You need not to worry whether you have studied the chapter before or not, does not matter. Okay, every single thing will be started from the basics only. All right. Someone is asking for how many hours this session will be. I have no idea how many hours it's going to take. Okay, I have no idea. We'll just start and see where we'll stop. Okay, we'll just start and see where we'll stop. So are you guys ready? Are you all ready for the session? I want some josh in the chats, fire in the chats. Are you all ready, people? Are you all ready? Yeah? Don't worry, guys, don't worry. We'll see what is going to be the duration of the session. Accordingly, if needed, we can break it into 2 parts as well. So don't worry. Okay? Don't worry about that. We can break this into 2 parts as well, because I know these are going to be some 6-7 chapters, right? If needed, we can break it into 2 sessions. Don't worry. All right, all right. So my dear students, in chemistry till now, we are done with class 12th physical. We are done with class 11th inorganic. We are done with class 11th organic. We are done with class 12th organic. And today we are going to be done with class 11th physical, right? After today's session, there will be only one part left. That is going to be class 12th inorganic chemistry. And that will be happening after 2 to 3 days. Okay? So don't worry about that as well. Yeah? All right, before starting the session, the question which I keep on asking you all the time, from which part of the country you guys are watching me right now? I want to know. I want to know this first of all in the chats. I want to know this first of all in the chats. From which part of the country you guys are watching me right now? Maharashtra, Kerala, Tamil Nadu, Srinagar, Jharkhand, Tamil Nadu, Karnataka, Bangalore, okay, Andhra Pradesh, Tamil Nadu, Kerala, Kashmir, Hyderabad, Meghalaya, okay, Delhi, and I want everyone to let me know this in the chats. All right, West Bengal. Okay, let me see the chats here first of all. Okay, someone is watching me from Baramulla, right? My neighborhood. All right, all right, all right. All right. Someone is watching us from USA. Wow. Yeah. Someone is watching us from UK. UK means Uttarakhand. All right, people. Amazing, amazing. Amazing. Perfect, perfect, perfect. Perfect. So should we start the session then? Are you all ready? First of all, tell me, has everyone smashed that like button? If not, do it right now. If not, do it right now, quick, quick, quick. If not, do it right now, quick. Are you done with that? So first of all, let me tell you the sequence of the chapters which we shall be following in the today's session. Okay, let me tell you the sequence of the chapters. My dear students, we are going to follow your NCERT sequence. We'll be starting with the mole. Then we'll be doing the atomic structure. Okay. After atomic structure, we'll be doing the redox. After redox, it's going to be your chemical equilibrium. After chemical equilibrium, it's going to be your ionic equilibrium. Okay. And once we are done with ionic, then at the end, it's going to be your thermodynamics. So this is going to be the sequence of the things which we are going to follow in the today's session. Okay. Sequence of the things which we are going to follow in the today's session. Just give me a second. I'm just fixing all these things. Just a second, people. Just a second. Give me a second. Yeah, it's perfect now. All right. Yeah, all the things are working properly. That's great. All right, one more thing, my dear students. The PDF of this particular session. I'll be sharing on my Telegram. If you are not the part of my Telegram yet, be the part of my Telegram channel quick. The name of the Telegram channel is Wassim Bhat Chemistry Official. Okay, WASSIMBHAT Chemistry Official is the Telegram channel name, wherein I'll be sharing the handwritten PDF of this particular session. All right? All right, people? All right? All right. So should we start? All ready? Yes, JEE students can also watch this. JEE students can also watch this. All right, Ayush, I'll do that. All right, Ayush, I'll do that. I'll follow that. I'll follow that. I'll follow that. Don't worry. Don't worry. I'll talk slowly. Yeah. Should we start then? Should we start, people? Should we start? Should we start? Quick, 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 everyone. Everyone means everyone. Perfect, perfect, perfect. Let's get going then. Let's get started with the first chapter of our today's session, which is going to be your epic mole concept. My dear students, this mole concept chapter, I will be starting with a simple statement. Okay? This mole concept chapter, I'll be starting with a simple statement. And the statement is going to be something like this. I'm writing here a term, 1 AMU, which is also what you call as 1U, which is also what you call as 1D. Okay? And we define it as 1 by 12th of, we define it as 1 by 12th of the mass of carbon-12 atom. 1 AMU, also called as 1U, also called as 1D, which is defined as 1 by 12th of the mass of carbon-12 atom, whose value is exactly 1.66 into 10 raised power minus 24 grams, or in terms of Avogadro's number, you can write it as 1 divided by Na. 1 divided by Na. This is the first statement which I would want every one of you to remember over here. My dear students, look at this AMU, which stands for atomic mass unit. atomic mass unit. This U over here, this stands for your unified mass. And this D over here, it stands for what? D stands for Dalton. D stands for Dalton. Okay. Now, my dear students, there are basically three basic terminologies which you must know first of all. And among those three basic terminologies, the first one is what you call as atomic mass. The second one is what you call as molecular mass. Molecular mass. And the third terminology is what you call as the molar mass. These are the three basic terminologies over here with which we are going to start this particular chapter. Atomic mass, molecular mass, and molar mass. So first of all, how do we exactly define the atomic mass? Atomic mass is nothing but, it is simply defined as the mass of one atom of an element. The mass of one atom of an element is what you call as atomic mass. Okay? Mass of one atom of an element is what you call as atomic mass. For example, if I talk about oxygen, what is the mass of one atom of oxygen? You must be knowing it is 16 AMU. 16 AMU. What does it mean? It means one atom of oxygen. It means one atom of oxygen is 16 times heavier than 1 AMU. It just means one atom of oxygen is 16 times heavier than 1 AMU. For example, if I talk about nitrogen, its atomic mass is 14 AMU. What does it mean? It means one atom of nitrogen is 14 times heavier than what? It is 14 times heavier than 1 AMU. Okay? So what is first of all your atomic mass? Atomic mass is nothing but mass of one atom of an element. Okay? Similarly, my dear students, how do you exactly define the molecular mass? Molecular mass, in simpler words, is defined as the mass of one molecule of a substance. The mass of one molecule of a substance. And how do we calculate this molecular mass? Simply, it is the sum of atomic masses. The sum of atomic masses of all the atoms present in the molecule. For example, have a look. If I talk about water, in case of water, how many elements do you see? My dear students, in case of water, you can see two elements. One is your hydrogen, one is your oxygen. What is the atomic mass of hydrogen? That's 1 AMU. How many hydrogen atoms do you see? 2 hydrogen atoms. What is the atomic mass of oxygen? 16 AMU. How many oxygen atoms do you see? 1 oxygen atom. If you calculate it, the value comes out to be either you write 18 AMU or you can write 18U. What does it mean? It means that one water molecule is 18 times heavier than 1 AMU. One water molecule is 18 times heavier than 1 AMU. As simple as that. For example, let's say I have got ammonia over here. Okay. For example, I want to calculate the molecular mass of ammonia. How do I calculate the molecular mass of ammonia? See, in case of ammonia, how many elements do you see here? 2 elements, nitrogen and hydrogen. Tell me one thing. In case of nitrogen, what is the atomic mass? The atomic mass of nitrogen is 14 AMU. How many nitrogen atoms do you see here? 1 nitrogen atom. What is the atomic mass of hydrogen? 1 AMU. How many hydrogen atoms do you see? 3 hydrogen atoms. The value comes out to be 17U. What does it mean? It means that one ammonia molecule is 17 times heavier than what? 17 times heavier than 1U over here or 1 AMU over here. Perfect? As simple as that. Similarly, my dear students, if you talk about the molar mass, how do we exactly define molar mass of the substance? Molar mass is nothing but, it is defined as the mass of 1 mole of a substance. It is defined as the mass of 1 mole of a substance. Or you can say, it is defined as the mass of 6.022 into 10 raised power 23 particles of the substance. Okay? For example, I want to calculate molar mass of this marker. What does that mean? That means I want to calculate mass of 1 mole marker. I want to calculate the mass of 6.022 into 10 raised power 23 markers. Okay? For example, I want to calculate molar mass of carbon. Molar mass of carbon is nothing but mass of 1 mole carbon. Or you can say mass of 6.022 into 10 raised power 23 carbon atoms. As simple as that. Okay? And my dear students, For example, if you talk about carbon, what is the atomic mass of carbon? Atomic mass of carbon is 12 AMU. If I ask you what is the molar mass of carbon, you just have to change the units. Instead of AMU, you just have to write 12 grams. Okay? For example, if I talk about oxygen, what is the atomic mass of oxygen? As I told you, 16 AMU. What will be the molar mass of oxygen? You just have to change the units. It's what you call as 16 grams. Okay? For example, talk about water. What is the molar mass of water? First of all, what is the molecular mass of water? 18U. Change the units. Instead of U, just write the grams. So 18 grams is the molar mass of water. That means this 12 grams is the mass of 1 mole of carbon. Okay? 12 grams is the mass of 1 mole of carbon. 16 grams is the mass of 1 mole of oxygen. 18 grams is the mass of 1 mole of water. So I believe all these three terminologies are absolutely clear to every one of you. Okay? One statement, my dear students, which I would want you guys to remember from now onwards. What is that? Remember, molar mass of the substance is always equal. Molar mass of the substance is always equal to mass of one particle of the substance, mass of one particle of the substance in grams, mass of one particle of the substance in grams multiplied by Avogadro's number. Remember this particular statement as well. For example, if you are given with a question, in which you are given with the mass of one particle of any substance, you are supposed to calculate its molar mass. What you just have to do, mass of one particle of the substance, you just have to multiply that with the Avogadro's number. Okay? For example, if I write a question here, if I write a small question here, the question is the mass of one atom of X. The mass of one atom of X is 4 into 10 raised power minus 23 grams. I'm asking you to calculate the molar mass of X. How you should be doing it? Quickly. My dear students, I'm supposed to calculate molar mass of X. And as I told you, molar mass of substance is equal to mass of one particle of the substance, which is 4 into 10 raised power minus 23 grams, multiplied by Avogadro's number, 6 into 10 raised power 23. This term cancel. The value comes out to be 24 grams. So 24 grams is nothing but it is the molar mass of X. As simple as that. Okay? Perfect. If molar mass is 24 grams, if molar mass of X is 24 grams, that means atomic mass of X would be 24 AMU. Atomic mass of X would be 24 AMU. Which element is there whose atomic mass is 24 AMU? That is magnesium. So you have identified the element as well. That means this X over here, it is which one? It is your magnesium. I believe I'm clear. If I'm clear, once in the chats, quick. If I'm clear, let me know once in the chats, quick. Now, my dear students, one more question which can be asked here. Look at the question carefully. The question is, if 1U is defined as 1 by 24th of the mass of carbon-12 atom, if 1U is defined as 1 by 24th of the mass of carbon-12 atom, then calculate the molecular mass of carbon dioxide on new scale. Understand what I'll be doing. My dear students, we already know 1U we have defined as 1 by 12th of the mass of carbon-12. 1U we have defined as 1 by 12th of the mass of carbon-12. Right? This is how we have defined 1U. Calling this equation number 1. As per the question, we have to change the standard. As per the question, we have to define 1U as 1 by 24th of the mass of carbon-12. We have to define 1U as 1 by 24th of the mass of carbon-12 atom. Okay? Which I'm now calling as U dash. Okay? My dear students, we are supposed to calculate the molecular mass of carbon dioxide as per new scale. That means we are supposed to calculate molecular mass of carbon dioxide as per U dash, not in terms of U. Okay? How exactly we solve these sort of questions? Remember what do I say here? Understand properly. My dear students, the first and the most important thing, Whenever you get this sort of a question, your first thing is going to be to get the relation between u and u dash. You need to first of all get the relation between u and u dash. Now, how do you get the relation between u and u dash? You just need to divide these two equations. Either divide 1 with 2 or divide 2 with 1. The choice is all yours. For example, if I divide equation 1 with equation 2, what do I get? I get u divided by u dash is equal to this term cancel. In the numerator, you have 1 by 12. In the denominator, you have 1 by 24. So I'll say u divided by u dash is nothing but 2. So I can say u is equal to 2 times u dash. So first part is done. You have got the relation between u and u dash. You got the relation between u and u dash. Now, once you get the relation between u and u dash, after that, my dear students, if I write molecular mass of what? Molecular mass of carbon dioxide. Let's first of all try to calculate the molecular mass of carbon dioxide as per our scale, as per u. And we know how do we do it. Carbon, its atomic mass is 12. There is one carbon atom. Oxygen, its atomic mass is 16. There are two oxygen atoms. The value comes out to be 44U. This is the molecular mass of carbon dioxide as per our scale, which we have chosen. Okay. But we do not have to write the answer in terms of u. We have to write the answer in terms of u dash. So what do I do here? This 44u I can write as 44 multiplied by 1u. And instead of this 1u, I can just write 2 times u dash. The value comes out to be 88u dash. So this 88u dash is nothing but it is the molecular mass of carbon dioxide as per new scale. I hope if this sort of a question comes into your exam, you should be in a position to solve this particular question. If yes, let me know once in the chats quick. Let me know once in the chats quick, people. Yeah? Perfect. Amazing. I want you guys to be active in the chat. So very, very, very active. All right, people. All right. Yes, Arjun, you can consult this. Yes, yes, yes. Perfect, guys. Perfect, perfect, perfect. Now, my dear students, there is something called as average atomic mass of the isotopic mixture. What does that mean? What does that mean? Hello, hello, Musab. Thank you so much. Okay. My dear students, first of all, let's say you have got an element X. The element is X. Okay. We have got the element X. Let's say this X has got two isotopes. Isotopes are the atoms of same element having same atomic number but different mass numbers. This is M1, this is M2. Okay. Let's say I've taken the element X. It has got two isotopes which have got same atomic number but different mass numbers. Remember, whenever you see any element having isotopes, for that particular element, what do we define? We define average atomic mass. For that element, we define average atomic mass. Now, my dear students, in order to calculate the average atomic mass, what do I need? I need the percentage abundances of the isotopes. I need the percentage abundances of the isotopes. What exactly are the percentage abundances? You'll get the idea in some time. First of all, remember just one thing. Whenever you see the element which has got isotopes, for that particular element, we do not define the normal atomic mass. What do we define? We define the average atomic mass. In order to calculate the average atomic mass, we need the percentage abundances of these isotopes. And the percentage abundances of the isotopes I represent with A and B, right? And once you get the value of A and B, you can just make one formula. Formula is M1A plus M2B divided by what? Divided by A plus B. This is one simple formula by means of which you can calculate the average atomic mass of an element which has got isotopes. For example, talk about chlorine. For example, talk about chlorine. If I ask you how many isotopes chlorine has, you will say chlorine has got two isotopes. One is Cl35, one is Cl37. Okay. If chlorine has two isotopes, I'm going to define average atomic mass for this chlorine. In order to calculate the average atomic mass of chlorine, what do I need exactly? I need percentage abundances of these isotopes. Let me tell you, it has been observed that the abundances of these isotopes is 75% and 25%. 75% and 25%. What does it mean basically? See guys, imagine that the room in which you guys are sitting right now, imagine there are total 100 chlorine atoms. Imagine there are total how many chlorine atoms? 100 chlorine atoms. Okay. Now, among those 100 chlorine atoms, there will be some of the chlorine atoms existing in the form of Cl35. Some of the chlorine atoms will be there in the form of Cl37. So basically, there are total 100 chlorine atoms in this room, and out of those 100 chlorine atoms, some of the chlorine atoms are Cl35 ones, and the other chlorine atoms are Cl37 ones. Now, these percentage abundances are telling me that out of the total 100 chlorine atoms, 75 of the chlorine atoms in this room will be which ones? Will be Cl35 ones. And the remaining 25 atoms will be which ones? Cl37 ones. As simple as that. Got it? So people, chlorine, it has got two isotopes. Okay. Now, since we got the percentage abundances of these isotopes, which we represent with A and B. Okay. This is the value of M1. This is the value of M2. If you got the value of A, B, M1, M2, the formula which I'll be using, that is M1A plus M2B divided by A plus B. What is the value of M1? 35. Sorry. M1 value is 35. What is the value of A? A value is 75. What is the value of M2? M2 value is 37. B value is 25. Divided by A plus B will come out to be 100. And when you solve this, the value comes out to be 35.5 AMU. So this 35.5 AMU is nothing but it is the average atomic mass of chlorine over here. I hope this is super clear to everyone. At the same time, my dear students, if you look carefully, abundance of this isotope is 75. Abundance of this isotope is 25. If you add them up, the value comes out to be 100. If you add them up, the value comes out to be 100. What does that mean? That means the sum of percentage abundances, of all the isotopes, of a particular element, is always equal to what? Is always equal to 100. Okay, remember this particular point as well. I believe I'm super clear to everyone. Now, if I'm clear, then you need to solve this question, which I've mentioned on the screen. This is the PYQ of JEE Mains, and I believe you can easily solve this. My dear students. If you look at the question carefully, we are given with the element boron, and boron has got two isotopes. One is B10, one is B11. These are the two isotopes of boron. My dear students, the percentage abundance of B10 is given to me as 19%, and the abundance of B11 is given to me as 81%. People, we represent these percentage abundances with A and B. This is the value of M1. This is the value of M2. I am supposed to calculate the value of M average, and you already know the formula, that is M1A plus M2B divided by A plus B, which is always 100. Right? What is the value of M1 here? The value of M1 here is 10. The value of A is 19. Plus, the value of M2 is 11. The value of B is 81. Divided by what? Divided by 100. And when you solve this, the value comes out to be 10.81 AMU. So this 10.81, what is it? It is the average atomic mass of boron, which I was supposed to calculate. I hope I am super clear to everyone. Yeah? I hope I'm super clear to everyone. If yes, let me know once in the chats. My dear students. Quick. Let me know quickly in the chats, people. Perfect. I hope if a question comes from this particular topic, I'm pretty much sure you should be in a position to solve that. You should be in a position to solve that. All right. Now comes one more basic thing. How do we calculate moles of different substances? My dear students, number of moles of a substance is equal to given mass of the substance in grams divided by molar mass of the substance. Given mass divided by molar mass. That gives me number of moles. Second one, number of moles of the substance is also equal to given number of particles of the substance divided by what? Divided by Avogadro's number. Given number of particles divided by Avogadro's number, that also gives me number of moles. The third formula, my dear students, number of moles of a gas. This formula is only valid for gases. And the gas should be present at STP. The gas should be present only at STP. See, number of moles of the gas at STP is always equal to given volume of the gas. Given volume of the gas in liters divided by what? Divided by 22.4 liters. These are the three basic formulas with the help of which we can calculate number of moles of a substance. Given mass divided by molar mass, given number of particles divided by Avogadro's number, given volume of the gas in liters divided by 22.4 liters. Okay. Now, if you remember these formulas, you can easily tell me the answers of these questions. Have a look exactly what I have come up with. Calculate the number of moles present in 160 grams of NaOH. So do you see I'm given with mass of substance, and whenever I'm given with mass of substance and I'm supposed to calculate moles, number of moles is equal to given mass of the substance in grams divided by molar mass of the substance. The value comes out to be 4, right? So basically, there are 4 moles present in 160 grams of NaOH. As simple as that. Look at the next one. Number of moles in 67.2 liters of carbon dioxide at STP. So I'm given with volume here. Whenever I'm given with volume and I'm supposed to calculate moles, it is given volume of the gas in liters divided by 22.4 liters. The value comes out to be 3. As simple as that. Okay. Look at the third one. I'm given with the number of particles, and whenever particles are given, moles are to be calculated. You are supposed to divide the given number of particles with the Avogadro's number. The value comes out to be 4. Similarly, my dear students, again you are given with the particles. And you are supposed to calculate moles. So it would be equal to given number of particles divided by what? Divided by Avogadro's number. The value comes out to be 80. So from these questions, you got to know how to convert mass into moles, how to convert volume into moles, how to convert particles into moles. I believe I'm clear to every one of you. If yes, let me know once in the chat quick. Yeah? I believe I'm clear to everyone. Perfect. Perfect, people. Now, guys, there is something important which you need to know. What is that? That is mole conversion diagram. From this diagram, some basic questions you can solve easily. And what are those basic questions? Try to understand properly. My dear students, as I told you, in order to calculate moles, either mass of the substance will be given to us, or number of particles of the substance will be given to us, or I'll say volume of the gas in liters at STP would be given to us. So in order to calculate moles, either mass would be given, or particles would be given, or volume of the gas would be given. Now, first of all, remember this. First of all, if mass is given, moles are to be calculated. Then what do we have to do? Given mass of the substance divided by molar mass of the substance. That gives me moles. Reverse of it. If moles are given, mass is to be calculated. If moles are given, mass is to be calculated. Then you are supposed to multiply moles with the molar mass of the substance. As simple as that. As simple as that. Similarly, if number of particles are given and I'm supposed to calculate moles, then given number of particles divided by Avogadro's number, that gives me moles. If moles are given, particles are to be calculated. If moles are given, particles are to be calculated, then moles are to be multiplied with the Avogadro's number. You'll be getting the particles. You'll be getting the particles. Similarly, my dear students, if volume is given, moles are to be calculated. If volume is given, moles are to be calculated. Then, given volume of the gas divided by 22.4 liters, that gives me moles. If you take the reverse of it, if moles are given, volume is to be calculated. Then moles are to be multiplied with 22.4 liters. If I'm clear with this diagram, let me know once in the chats quickly, people. Everyone. Let me know once in the chats, people, quickly. Let me know quickly in the chats, my dear students. Everyone. Let me know once in the chats quickly. Thank you, Farhad. Thank you, thank you. Yeah? I hope this is super clear to everyone. I hope this is super clear to everyone. Is it? Is it? Is it? Quickly, quickly. All right, amazing. Now we will try to understand few things. Try to understand few things. Let's say you are given with a question in which mass of the substance is given and volume is to be calculated. Let's say you are given with a question in which mass of the substance is given and volume is to be calculated. So you have to convert mass into volume. You have to convert mass into volume. What do you do at that time? See, there is no direct arrow between mass and volume. There is no direct arrow between mass and volume. So if mass is given, volume is to be calculated. What do you do? We'll start from mass and we'll try to end at volume. We'll start at mass, we'll try to end at volume. So I'll be following all those arrows which are going to take me from mass till volume. I'm going to follow all the arrows which are going to take me from mass till volume. So which all arrows I'll be following? From mass till moles first, then from moles till volume. So I'll have to follow two arrows. So there'll be two steps exactly. First step, given mass divided by molar mass. That will give me moles. Moles multiplied by 22.4 liters. That will give me volume. Perfect. Let's say mass is given, particles are to be calculated. Mass is given, for example, particles are to be calculated. I'll be starting from mass and I'll have to reach till particles. I'll have to reach till particles. I'll be following all those arrows which take me from mass till particles. Okay. So how many arrows are there? There are two arrows. First thing, given mass divided by molar mass will give me moles. Moles multiplied by Avogadro's number, that will give me particles. Perfect. As simple as that. If, for example, volume is given, particles are to be calculated. I'll be starting from volume. I'll have to reach till particles. I'll be following all the arrows which take me from volume till particles. So my first step is going to be given volume divided by 22.4. That gives me moles. Moles multiplied by Avogadro's number. That gives me particles. As simple as that. Okay. Let me give you one question so that you can understand what exactly am I talking about. Look at this simple question, guys. The question is, calculate the volume of 128 grams of carbon dioxide at STP. Calculate the volume of 128 grams of carbon dioxide at STP. I'm given with mass. I'm supposed to calculate volume. I am given with mass. I'm supposed to calculate volume. How much I'm given with? 128 grams. I'm given with mass. I'm supposed to calculate volume. I'm given with mass. I'm supposed to calculate volume. Okay. So my first step is given mass divided by molar mass will give me moles. Then moles multiplied by 22.4. That will give me volume. Perfect. So just two steps are there. My first step is number of moles of carbon dioxide is equal. Okay, let me just change the values here. Let's not use 128. You can write 132 grams. so that our calculation would be easy a bit. So number of moles is equal to given mass of the gas divided by molar mass of the gas. Molar mass of carbon dioxide is 44. The value comes out to be how much? 3. So I've calculated moles. Second step is moles multiplied by 22.4. Moles multiplied by 22.4 liters. That will give me volume. So moles of carbon dioxide multiplied by 22.4 liters. That is 3 multiplied by 22.4 liters. The value comes out to be 67.2 liters. So this is how you have converted mass into volume. If I'm clear, let me know once in the chats quick. Yeah? I hope this is very much clear to you. My dear students, if you look at this question, the mass of one atom of X, is this. The mass of one atom of X is this. Calculate the number of moles present in 96 kg of X. Calculate the number of moles present in 96 kg of X. So, we are supposed to calculate number of moles of X, which would be equal to given mass of X in grams divided by molar mass of X. Okay, what is given mass of X? It is 96 kg means 96,000 grams divided by. I just need to calculate molar mass of X. But I'm not given with the molar mass of X. I am given with mass of one atom of X. If I am given with mass of one atom of X, I can easily calculate molar mass, which is mass of one atom of X multiplied by Avogadro's number. Few minutes back only I told you. So this term cancel. The value comes out to be 24 grams. So this is molar mass of X. This is molar mass of X. So what I have to do? Given mass of X in grams divided by the molar mass of X, which is 24 grams. The value comes out to be 4,000. So these are the total number of moles. These are the total number of moles which are present in 96 kg of X. Am I clear with this question as well? Am I clear with this question as well? Quickly in the chats, people. Everyone, I'm looking at your chats only. Everyone. Yeah? Perfect. Now, my dear students, there is one more set of questions. There is one more set of questions which is asked from mole. One more set of questions in which you will be asked to calculate either atoms or electrons or protons or neutrons or valence electrons. Anything can be asked. Okay. Whenever you see a question based on atoms, electrons, protons, neutrons, ions, valence electrons, there is one more simple diagram which you have to follow. What is that diagram? What is that diagram? See guys, I'm writing here a term, given quantity. Whatever would be given to us in the question, whatever would be given to us in the question, whether we are given with mass of substance, whether we are given with the particles of the substance, or will be given with the volume of the substance, whatever stuff is given to us in the question, that is something I'll be calling as given quantity. Whatever thing is given to us, given quantity. Okay. The first step always is to convert given quantity into number of moles. First step always is going to be conversion of given quantity into number of moles. Second step, moles multiplied by Avogadro's number. Second step, you're supposed to multiply moles with what? Avogadro's number. And remember, if the given substance is in molecular form, then moles multiplied by Avogadro's number, that gives me molecules. Moles multiplied by Avogadro's number, what does that give me? That gives me molecules, number of molecules. Okay. But remember, if the given substance is, for example, in atomic form, then moles multiplied by Avogadro's number, that does not give me molecules, that gives me number of atoms. And if the given substance is in ionic form, then remember, moles multiplied by Avogadro's number, that gives me ions directly. You have to remember this stuff. Okay. Generally, my dear students, the given substance will be in molecular form. If the given substance is in molecular form, then moles multiplied by Avogadro's number, that gives me molecules. Once you are done with the calculation of molecules, then you can easily calculate atoms, electrons, protons, neutrons, valence electrons, etc., etc. Whatever stuff is asked out of these, you have to just follow this diagram. Given quantity into number of moles, moles multiplied by Avogadro's number, right? That can give you either molecules or atoms or ions, depending on whether the given substance is in molecular form, atomic form, or even ionic form. All right? Perfect. Perfect, people. Now let me show you one example so that this particular topic gets clear to you. Let's have a look on this question. My dear students, calculate the number of atoms, electrons, protons, neutrons present in 44.8 liters of carbon dioxide at STP. Identify your given quantity firstly. Your given quantity is volume. We are given with volume. My first step is always conversion of given quantity into moles. So, first of all, I'll be calculating number of moles of carbon dioxide, which is given volume of carbon dioxide in liters divided by 22.4. The value comes out to be 2. So I've calculated moles. Second step is moles multiplied by Avogadro's number. First of all, look at the substance. The substance is in molecular form. If the substance is in molecular form, then moles multiplied by Avogadro's number, what does it give me? It gives me molecules. So I have calculated the molecules of carbon dioxide here. So how many molecules of carbon dioxide do we have here? 2 Na. We have got 2 Na molecules of carbon dioxide. So since we have done the question till molecules, now comes your atoms. First of all, if I ask you the general information about one molecule of carbon dioxide, tell me in one molecule of carbon dioxide how many atoms are there? If you look carefully, in one molecule of carbon dioxide there are exactly how many atoms? There are 3 atoms, correct? In one molecule of carbon dioxide, there are 3 atoms. Similarly, in one molecule of carbon dioxide, if I ask you how many electrons are there? Carbon has got 6 electrons, oxygen 8 electrons, So in one molecule of carbon dioxide, there are 22 electrons. Okay. How many protons? There are 22 protons. How many neutrons? 12 minus 6 is equal to 6. 16 minus 8 is equal to 8. 16 minus 8 is equal to 8. So there are 22 neutrons as well. So I got to know in one molecule carbon dioxide, there are 22 electrons, 22 protons, as well as 22 neutrons. I'm talking about one molecule of carbon dioxide. Now, people, it's pretty much clear. If one molecule carbon dioxide contains 3 atoms, 2 molecules of carbon dioxide will contain multiplied by 2. 3 molecules of carbon dioxide multiplied by 3. 4 molecules multiplied by 4. How many molecules do we have? 2 Na. So 2 Na molecules of carbon dioxide will contain 3 into 2 Na. That comes out to be 6 Na atoms. 22 multiplied by 2 Na. 44 Na electrons. Similarly, 44 Na protons. Similarly, 44 Na neutrons. Am I clear with this? Let me know once in the chats if it is super clear to everyone. Yeah? Perfect. I believe it is super clear to every one of you. If yes, I would want to know first of all in the chats. Quickly, people. I would want to know first of all in the chats if all the things are super clear over here. Everyone, I want you guys to be active in the chats, guys. Otherwise, it's not going to be fun. Abid, it's not my birthday today. My birthday was on 6th of April, okay? Thank you for the belated wishes. Yeah? Perfect. Clear? Let me give you one more question. And let me check whether you can solve this or not. The question is pretty much simple, and this is the PYQ. This has been asked in I believe in NEET 2021 or 20 or 22 from those years. Okay, you can check it out afterwards. Anyways, no need to check. Let's try to handle this question. The question is calculate the valence electrons present in 4.2 grams of N3 negative. Calculate the number of valence electrons present in 4.2 grams of N3 negative. So in this question, I'm supposed to calculate valence electrons. What is the first step which I'll be doing? Calculation of moles. Number of moles of N tri-negative is equal. Given mass of N tri-negative divided by molar mass of nitrogen, the value comes out to be 0.3. Second step, moles multiplied by Avogadro's number. Moles multiplied by Avogadro's number. That gives me either atoms or molecules or ions. Now, first of all, see, what is the state of this N tri-negative? Is it in molecular form? Is it in atomic form? Is it in ionic form? What exactly? I'll say it is in ionic form. If the given substance is in ionic form, then moles multiplied by Avogadro's number, what does that give me? That gives me number of ions. So I got number of ions of N tri-negative. I got number of ions of N tri-negative. Now, my dear students, since we have got these many ions of N tri-negative, tell me in one N tri-negative, how many electrons are there? 7 plus 3. In one N tri-negative, there are 10 electrons. In one N tri-negative, there are 10 electrons. Out of 10 electrons, 2 electrons will go in the first shell and 8 electrons will go in the second shell. The second shell here, I'll be calling as valence shell. And the number of electrons present in the valence shell, I'm calling them as the valence electrons. I'm calling them as the valence electrons. So can I say, in one ion, I got to know in one ion of N tri-negative, how many valence electrons are there? 8 valence electrons. If in one ion there are 8 valence electrons, in 2 ions multiplied by 2, in 3 ions multiplied by 3, how many ions do we have? 0.3 Na. So in 0.3 Na ions, how many valence electrons do we have? 8 multiplied by 0.3 Na. The value exactly comes out to be 2.4 Na valence electrons. If I am clear, let me know once in the chats. So these are the total number of valence electrons which are present in 4.2 grams of N3 negative. Yeah? Am I clear to everyone, people? Let me know once in the chats quick. Let me know once in the chats quick. Someone is saying how it is 2 and 8. See, first shell always accommodates 2 electrons. Second shell accommodates 8 electrons. After, I have no idea how long the session will go. It can go for 8 hours, 10 hours, 12 hours. No idea. Let's see. Yeah? I believe this is super clear to everyone. Okay. Now, my dear students, let's come to the main topic of your mole concept, from which questions are almost every year asked. What is that? That is stoichiometry. That is stoichiometry. Let's exactly know what happens in this stoichiometry. See, guys. First of all, just to make you understand, I'm going to take a general reaction. The reaction is like this. N2 gas plus H2 gas. What does it give me? It gives me NH3 gas. This is one general reaction. Okay. The first thing, my dear students, which you are supposed to do in stoichiometry, you are supposed to balance the reaction. Is this reaction balanced? No, the reaction is not at all balanced. Now, if the reaction is not balanced, then we are supposed to balance the reaction first. So try to balance it. This will be 3 times. This will be 2 times. This will be once. Okay. So first of all, this 1, 3, and 2. This 1, 3, and 2 is what I call as, these are what I call as stoichiometric coefficients. These are what I call as stoichiometric coefficients. And my dear students, remember, stoichiometric coefficients are treated as moles. They are treated as moles. Now, these stoichiometric coefficients are telling me that 1 mole of N2 completely reacts with 3 moles of H2 and produces 2 moles of NH3. Okay. This information I got to know only when the reaction was balanced. If the reaction was not balanced, then I could not have gotten this particular statement over here. Right? Right, my dear students? So, stoichiometry is telling us that 1 mole N2 completely reacts with 3 moles of H2 and produces 2 moles of NH3. This particular statement I wrote only and only in terms of moles. I wrote this particular statement in terms of moles. Now, people, I am going to write one more statement in terms of mass. How exactly? Have a look. If I ask you what is the molar mass of N2, if I ask you what is the molar mass of N2, molar mass of N2 is 28 grams. Molar mass of N2 is 28 grams. That means mass of 1 mole of N2 is 28 grams. Do we have 1 mole of N2? Yes. So what is the mass of 1 mole of N2? As I told you, it's 28 grams. So I'm just writing 28 grams of N2. What is the molar mass of H2? Molar mass of H2 is 2 grams. That means mass of 1 mole of H2 is 2 grams. That means mass of 1 mole of H2 is 2 grams. But do I have 1 mole of H2 or 3 moles? I have 3 moles of H2. If the mass of 1 mole of H2 is 2 grams, therefore mass of 3 moles of H2 would be 6 grams. So 6 grams of H2. What is the molar mass of NH3? 17 grams. Okay. That means mass of 1 mole of NH3 is 17 grams. If the mass of 1 mole NH3 is 17 grams, therefore the mass of 2 moles of NH3 would be 34 grams. 34 grams of what? NH3. So I can say stoichiometry is again telling us that 28 grams of N2 completely reacts with 6 grams of H2 and produces 34 grams of NH3. And as you saw, this statement over here, I wrote in terms of mass. This statement over here, I wrote in terms of mass. Again, I'll be writing one statement which will be directly in terms of volume. I can treat these stoichiometric coefficients directly as volume. I can say 1 liter N2 completely reacts with 3 liters of H2 and produces 2 liters of NH3. And this particular statement I directly wrote in terms of volume over here. So my dear students, remember, in stoichiometry, you should be in a position to write all these 3 statements. Whatever reaction is given to you, whatever reaction is given to you, for every reaction, you should be in a position to write these different statements. One in terms of moles, one in terms of mass, one in terms of volume. If you can do that, let me know once in the chats quick. If you can do that, let me know once in the chats quick. I'm looking at your chats only. I am looking at your chats, people. Quickly. Everyone. Everyone means everyone. Quick. Everyone means everyone. Quick. Quickly, my dear students. Yeah? Perfect. Now, my dear students, what kind of questions are asked from stoichiometry? Have a look exactly. Have a look exactly. You'll get to know what kind of questions are asked from stoichiometry. Guys, I'll give you the break exactly at 10. Okay? So please and please do not ask me the break till 10. At 10, we'll take the dinner break. Okay? We'll have food at 10. Not before that. So please stop asking breaks in between the session. It keeps on distracting. Okay? It's my keen request to all of you. All right? Okay? The break will be exactly given at 10 p.m. So 1 more hour. Perfect. Look at the stoichiometry, my dear students. The question is, calculate the mass of O2 gas produced on heating 12.25 grams of KClO3. As per the question, we are going to heat up KClO3. And remember, when KClO3 is heated, it breaks down into KCl and it gives O2 gas. When KClO3 is heated, it breaks down into KCl and it produces O2 gas. As per the question, my dear students, as per the question, we are going to heat up 12.25 grams of KClO3. Now the question is asked, on heating 12.25 grams of KClO3, what mass of O2 is produced? What mass of O2 is produced? My dear students, whenever you are given with a question in stoichiometry, the first and the most important thing, balance the reaction. So this is 2, this is 2, this is 3. The reaction is balanced. After balancing the reaction, whatever is the given quantity, whatever is the given quantity. Convert the given quantity into number of moles. Convert the given quantity into number of moles. I am given with mass of KClO3. I'm given with mass of KClO3. So get the number of moles of KClO3 first, which is given mass of KClO3 divided by what? Divided by molar mass of KClO3. The value comes out to be 0.1. So technically, I am going to heat up 0.1 moles of KClO3. Technically, I'm going to heat up 0.1 moles of KClO3. Now, my dear students, stoichiometry is telling me that 2 moles of KClO3. Stoichiometry is telling us that when 2 moles of KClO3 are heated, 3 moles of O2 are produced. This is something which stoichiometry is telling me. When 2 moles of KClO3 are heated, 3 moles of O2 are produced. Therefore, when 1 mole KClO3 is heated, how many moles of O2 would be produced? I would say 3 by 2 moles of O2 would be produced. But as per the question, do I have to heat up 1 mole KClO3? No. As per the question, I have to heat up 0.1 moles of KClO3. So when 0.1 mole KClO3 is heated, 3 by 2 multiplied by 0.1, I will say 0.15 moles of O2 would be produced. So I got to know the moles of O2 which are produced when we heat up 0.1 moles of KClO3. But as per the question, am I supposed to calculate the moles of O2 produced? No. I am supposed to calculate mass of O2 produced. And how do you convert moles into mass? Simple. Moles multiplied by its molar mass. The value comes out to be 4.8 grams. So I got to know 4.8 grams. I got to know 4.8 grams of O2 are produced upon heating 0.1 moles of KClO3, upon heating 12.25 grams of KClO3. Am I clear to everyone? If yes, let me know once in the chat quick. If yes, let me know in the chats quick. Sir, how to download your notes? I keep on sharing my notes on my Telegram. The Telegram channel name is, this is the Telegram channel name, Wassim Bhat Chemistry Official. This is the Telegram channel name. Okay, join this Telegram channel. I keep on sharing all my notes on this particular Telegram channel. For the ones who are not the part of my Telegram and who want to get the notes and stuff. Yeah? Perfect. Am I clear, people? Am I clear? Am I clear? Look at one more question. Look at one more question, my dear students. The question is, calculate the volume of carbon dioxide gas produced. Okay. All right. One thing, guys. Before solving this question, let me tell you one more thing. Before solving this question, I need to tell you one thing. What is that? Whenever you have got the organic compound containing carbon and hydrogen, whenever you see an organic compound containing carbon and hydrogen, whenever this particular compound undergoes combustion, remember, its products are always carbon dioxide and water. Okay? Whenever the organic compound containing carbon and hydrogen undergoes complete combustion, it leads to the formation of carbon dioxide and water. Similarly, remember, whenever you have got an organic compound in this form, CXHYOZ, an organic compound containing carbon, hydrogen, oxygen. When this particular compound undergoes combustion, it again leads to the formation of carbon dioxide and water. Now, my dear students, there's a simple way to balance these combustion reactions. There's a simple way to balance these combustion reactions. Say, this X, I'll keep the stoichiometric coefficient here. This Y, I'll take and I'll keep Y by 2 here. The stoichiometric coefficient of O2 will be X plus Y by 4. Remember this directly. Remember this directly. 1, X plus Y by 4, X, Y by 2. Okay, look at this one. This is X, so keep the stoichiometric coefficient here. This is Y, make Y by 2 here. Make Y by 2 here. The coefficient of O2 would be X plus Y by 4 minus Z by 2. X plus Y by 4 minus Z by 2. So this is the way by means of which you can balance these reactions. This is the way by means of which you can balance these reactions. And you need to look at this particular question now. As per the question, we are going to do the combustion of 570 grams of octane. As for the question, we are going to do the combustion of 570 grams of octane. What is the molecular formula of octane? C8H18. And you are going to do its combustion. It will lead to the formation of carbon dioxide. And with carbon dioxide, we get water. With carbon dioxide, we get water. As per the question, we are going to do the combustion of 570 grams of octane. Okay. What is the first thing which we do in stoichiometry? We balance the reaction. We balance the reaction. If this is 8 here, make this as 8. If this is 18, 18 divided by 2 is 9. This would be x plus y by 4. The value comes out to be 25 by 2. And this coefficient would be 1. Now, after balancing the reaction, my dear students, after balancing the reaction, we are supposed to convert the given quantity into number of moles. This is my given quantity. I'm given with mass of octane. So first thing, I'm supposed to convert mass of octane into moles of octane. So moles of octane is equal to given mass of octane divided by molar mass of octane. The value comes out to be 5. The value comes out to be 5. So technically, we are going to do the combustion of 5 moles of octane. Technically, we are going to do the combustion of 5 moles of octane. Now, my dear students, the coefficient here is 1. The coefficient here is 8. So can I say stoichiometry is telling us that 1 mole octane upon combustion produces 5 moles of carbon dioxide. 1 mole octane upon combustion produces 5 moles of carbon dioxide. But if you look carefully, do I want to do the combustion of 1 mole of octane or 5 moles of octane? We have to do the combustion of 5 moles of octane. And when 5 moles of octane undergoes combustion, when 5 moles of octane, sorry, this is not 5 here, this is 8. This is 8. Okay. 1 mole octane, when it undergoes combustion, 8 moles of carbon dioxide are produced. Therefore, when 5 moles of octane undergoes combustion, 8 multiplied by 5, that means 40 moles of carbon dioxide are produced. So I would say these are the moles of carbon dioxide produced. These are the moles of carbon dioxide produced when we do the combustion of 5 moles of octane. But as per the question, do I need to calculate moles of carbon dioxide produced? No. I need to calculate volume of carbon dioxide produced. How do you convert moles into volume at STP? I'll say volume of carbon dioxide produced is equal to moles of carbon dioxide produced multiplied by 22.4 liters. The value comes out to be 896 liters. So I would say 896 liters of carbon dioxide is produced during the combustion of 5 moles of octane, during the combustion of 570 grams of octane. If I'm clear to everyone, you can let me know quickly in the chats. You can let me know quickly in the chats. Yes? Quickly, my dear students, everyone, quickly. Everyone in the chats, quick. Yeah? My dear students, the most important topic of the chapter, what is that? That is limiting reagent. What is limiting reagent exactly? What is limiting reagent? I would say limiting reagent is basically that reactant. It is basically that reactant which gets completely consumed. Which gets completely consumed earlier in the reaction. That reactant which gets completely consumed earlier in the reaction. What does that mean? Have a look. Have a look, my dear students. For example, you have got the reaction like this. A plus B, it has to give C and D. Let's say this is the reaction. Okay? Let's say this is the reaction. It's a balanced chemical equation, for example. Let's say at time t is equal to 0, I'm starting with 10 moles of A and 5 moles of B. Let's say initially at time t is equal to 0, I'm starting with 10 moles of A and 5 moles of B. Since I'm writing time t is equal to 0, that means reaction has not started yet. If reaction has not started, that means product formation has not taken place yet. That means product formation has not taken place yet. So I would say in the container, moles of C right now and moles of D right now would be 0 because the reaction has not started yet. Now, once the reaction will start, these reactants, they will start to disappear. They'll start to get consumed, okay? And the moles of products, they'll start to get formed. So basically, as the reaction starts, moles of reactants keeps on decreasing. Moles of products will keep on increasing. Now, as the reaction starts, moles of reactants are keeping decreasing. Can I say among these two reactants, there would be one reactant which will be getting consumed earlier in the reaction, completely consumed? What do you call that as? Limiting reagent. So I would say your B over here is going to be your limiting reagent, which would be getting completely consumed earlier. Okay. If B is the limiting reagent, it has got completely consumed. If B is limiting, I will be calling this A as the excessive reagent. Now, my dear students, since A is excessive reagent, so that means out of 10 moles of A, there will be some of the moles of A still present in the container. When B would have got completely consumed, at that point of time, there will be some moles of A present in the container, right? Because A is the excess reagent. Now, similarly, some moles of D would have got formed and some moles of C would have got formed. And at this particular point of time, the reaction would have stopped. Now the point comes, how many moles of C have got formed? How many moles of D have got formed? How many moles of A are still left in the container? All that information is provided by the limiting reagent. Okay? How exactly? Try to understand very clearly what I'm going to tell you now. My dear students, for example, you have got the reaction like this. N2 gas plus H2 gas. It gives us NH3 gas. This is, for example, your reaction. Now, for example, I'm starting with 10 moles of N2 as well as 10 moles of H2. So in the beginning, there will be 0 moles of NH3 because the reaction has not started yet. Now, my dear students, whenever you are given with the amounts of all the reactants, at that point of time, we use the concept of limiting reagent. Okay? And in the limiting reagent concept, what is the first thing which we do? We are supposed to balance the reaction. Now the reaction is balanced. So the first thing in the limiting reagent concept, we are supposed to balance the reaction. Once we balance the reaction, we are supposed to identify. What? We are supposed to identify the limiting reagent. How do we identify the limiting reagent? See, this 10 divided by its stoichiometric coefficient is 1. This 10 divided by its stoichiometric coefficient is 3. The value comes out to be 3.33. The value comes out to be 10. Which one is lesser value? 3.33 is lesser value. The one that gets the lesser value, that's always your limiting reagent. If one is limiting, other one is excess. Okay? So how do you identify the limiting reagent? Divide the given moles of reactants. By the respective stoichiometric coefficients. The one that gets the lesser value, that's always going to be your limiting reagent. Yeah? That's always going to be your limiting reagent. So which one is my limiting reagent here? I would say this H2 is my limiting reagent. If H2 is the limiting reagent, it would have got completely consumed. So there will be 0 moles of H2 left in the container. And when H2 would have got completely consumed, at that point of time, the reaction would have stopped. Now, all the information. What information? Moles of product formed. Moles of excess reagent left. All that information is provided by the limiting reagent. How exactly? Have a look. The stoichiometric coefficient here is 3. Here it is 2. As per the stoichiometry of the reaction, I can say 3 moles of H2. Gives 2 moles of NH3. 3 moles of limiting reagent gives 2 moles of NH3. Therefore, 1 mole of limiting reagent gives 2 by 3 moles of NH3. But do I have 1 mole of limiting reagent or 10 moles? I can say 10 moles of limiting reagent gives 2 by 3 multiplied by 10. The value comes out to be 6.66 moles of NH3. So I got to know at the end of the reaction. 6.66 moles of NH3 have got formed. Did you see how I checked that? entire product formation is decided by limiting reagent. 3 moles are giving 2 moles. 1 mole will give 2 by 3 moles. 10 moles will give 2 by 3 into 10. Simple. Similarly, how many moles of excessive reagent are left? How many moles of excessive reagent are left? My dear students, first of all, this is 3 here. This is 1. So I can write a statement. 3 moles of limiting reagent reacts with, I'm using the term reacts with. 3 moles of limiting reagent reacts with 1 mole of excess reagent, 1 mole of N2. If 3 moles of limiting reagent reacts with 1 mole of N2, therefore 1 mole of limiting reagent would have reacted with 1 by 3 moles of N2. Okay, so eventually 10 moles of limiting reagent, 10 moles of limiting reagent would have reacted with 1 by 3 multiplied by 10. The value is 3.33 moles of N2. So I got to know out of 10 moles of N2, 3.33 moles of N2 are reacting. So how many moles of N2 would be left? 10 minus 3.33, the value would be 6.66. So these are the moles of N2 left in the container at the end of the reaction. Am I clear? Quickly, let me know in the chats. Quickly, let me know in the chats if I'm clear till here. Everyone, my dear students, with some fire emojis, quick. Let me check your chats on the screen. Let me check your chats on the screen. Everybody. Am I clear till here? Quickly, everyone. You're supposed to be very, very, very active, my dear students. Yeah? Perfect. 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 Everyone, quick. Thank you, Abhinish. Thank you. Amazing. Now, people, let's get going. Let's see your questions so that you can understand things properly. For example, you have got a question here. From this question, every single thing will be clear again. From this question, every single thing will be clear again. Look at the question carefully. We are given with the reaction in the balanced format. 6 times LiH plus 8 times BF3. It gives me 6 times LiBF4. And with this, I'm writing B2H6, right? This is my reaction. Now, my dear students, as per the question, we are starting with 2 moles each of reactants. We are starting with 2 moles each of reactants. So this is going to be 0, this is going to be 0. Now, since the reaction is balanced, I'm supposed to identify the limiting reagent. How do I identify? Divide the given moles by the respective stoichiometry coefficients. The one that gets the lesser value is always the limiting reagent. So if this is limiting, this is excess. So I got to know my limiting reagent. My limiting reagent is BF3. Even if BF3 is my limiting reagent, it would have got completely consumed. So I'll be left with nothing here. Now, entire product formation is decided by the limiting reagent. As per the question, what am I supposed to calculate? I'm supposed to calculate the moles of B2H6 formed. I'm supposed to calculate moles of B2H6 formed. How am I going to calculate that? Limiting reagent is going to give me the information about that. Coefficient here is 8, and it is 1. So I can say 8 moles of BF3 gives me 1 mole. So 1 mole of BF3 gives me 1 by 8 moles. So 2 moles of BF3 gives me multiplied by 2. The value is 1 by 4. So I will say 0.25 moles of BF3, 0.25 moles of B2H6 have got formed at the end of the reaction. If I'm clear, let me know once in the chats quick. If I'm clear, let me know once in the chats quick. See, a basic question. Can you tell me which one is the limiting reagent? 3 moles of NaOH. As per the question, 3 moles of NaOH reacts with 4 moles of H2SO4. You have to find the limiting reagent. I want your answer in the chats. I want your answer in the chats. Quick. I want your answer in the chats, my dear students. I want your answer in the chats, everybody. Guys, you should be in a position to check it. Quickly. People are saying NaOH, huh? Let me check. So 3 divided by 2, 4 divided by 1. 3 divided by 2 is 1.5, 4 by 1 is 4. Which one is lesser? 1.5. So NaOH is my limiting reagent. All of you are perfectly correct. Amazing. Good. All right. Perfectly done. Great job, guys. Great job. Now, my dear students, there is something called as percentage yield, from which one question is asked. What is this percentage yield? What is this? What is this percentage yield? First of all, if I talk about percentage yield is always equal to, just a second. Percentage yield of the reaction is always equal to experimental, or you call it as the actual amount, experimental or actual amount, divided by expected or theoretical amount, multiplied by 100. This is how you calculate percentage yield of the reaction. Experimental amount divided by expected amount multiplied by 100. My dear students, two things you have to know. Experimental amount would be given in the question. Expected amount you'll be calculating with the help of what? Expected amount you'll be calculating with the help of stoichiometry. Okay. Experimental amount would be given to us in the question. Expected amount will be calculating with the help of stoichiometry, and once we get the two amounts, we can easily calculate the percentage yield. How exactly? Let's have a look. My dear students, we have got a question. On heating 40 grams of calcium carbonate, as per the question, on heating 40 grams of calcium carbonate, 20 grams of calcium oxide is produced. The question says that on heating 40 grams of calcium carbonate, 20 grams of calcium oxide is produced. So this is the data which is experimentally verified in the question. Okay? It's experimentally verified data. It has been checked in the lab maybe, that when you heat up 40 grams of calcium carbonate, 20 grams of calcium oxide is produced. So this 20 grams, is it the experimental amount or actual? It is the experimental or expected? It is the experimental amount. In order to get the yield, we need two amounts. Experimental, that's given to us in the question. Expected with the help of stoichiometry. Have a look properly what I'll be doing. What is the mass of 1 mole calcium carbonate? 100 grams. Okay. What is the mass of 1 mole calcium oxide? 56 grams. So can I say, my dear students, 100 gram calcium carbonate upon heating, produces 56 grams of calcium oxide. This is something which stoichiometry is telling me, that when you heat up 100 grams of calcium carbonate, 56 grams of calcium oxide should produce. This is stoichiometry telling me that. Okay. Therefore, when 1 gram calcium carbonate is heated, how many grams of calcium oxide should produce? 56 divided by 100 grams of calcium oxide should produce. Therefore, when 40 grams of calcium carbonate is heated, how many grams of calcium oxide should produce? Multiplied by 40 grams of calcium oxide. When you solve this particular term, the value comes out to be 22.4 grams. So I got to know with the help of stoichiometry, On heating 40 grams of calcium carbonate, 22.4 grams of calcium oxide should produce. So this is something which stoichiometry is telling me, and stoichiometry always give me which amount? Expected amount. So I got the experimental amount, I got the expected amount, right? So percentage yield is equal to experimental divided by expected multiplied by 100. You can directly say yield of the reaction is how much? 89%. Yield of the reaction is how much? 89%. If I am clear, let me know once in the chat quick. Let me know once in the chat quick, my dear students, if I'm clear with this. Okay. Now, my dear students, here is one more thing which is asked. What is that? Let me show that to you. Just a second. Just a second. What is that? That is mass percentage of an element. Mass percentage of an element in a compound. Mass percentage of an element in a compound. It is always equal to molar mass of the element multiplied by Z, molar mass of compound multiplied by 100. What it means exactly, what these terminologies are. Try to understand very clearly what I'll be saying. Try to understand very clearly what I'll be saying. Someone is saying, sir, it was 2.24. It's not 2.24, it's 22.4. I've solved the question 1,000 times. Okay. All right. Have a look on this, my dear students. For example, I'm talking about glucose, C6H12O6. C6H12O6. Okay. In case of glucose, how many elements do we see? In case of glucose, there are 3 elements: carbon, hydrogen, and oxygen. Let's say, my dear students, let's say I want to know the mass percentage of carbon in glucose. Let's say I want to know the mass percentage of carbon in glucose. Okay. Mass percentage of carbon in glucose. How do you get the mass percentage of carbon in glucose? Have a look. What is the molar mass of carbon? 12. Okay. 1 mole glucose contains how many moles of carbon? 1 mole glucose contains 6 moles of carbon. Divided by. What is the molar mass of this entire compound? 180 multiplied by 100. Solve this. It will give you the mass percentage of carbon in glucose. It will give you the mass percentage of carbon in glucose. For example, I want to know the mass percentage of hydrogen in glucose. What is the molar mass of hydrogen? 1. Right? In 1 mole glucose, how many hydrogens do you see here? 12H divided by. What is the molar mass of this entire compound? 180 multiplied by 100. This will give me the mass percentage of hydrogen in glucose. Simple. For example, I want to know the mass percentage of oxygen in glucose. Okay. What is the molar mass of oxygen? 16 grams. In 1 mole glucose, how many moles of O do you see? 6 divided by. What is the molar mass of glucose? 180 multiplied by 100. This will give me the mass percentage of oxygen in glucose. As simple as that. Right? Am I clear with this? Am I clear with this, people? So like this, these basic questions are asked. For example, you will be given with a compound, and in the compound, you will have to calculate the mass percentage of different elements. You can do that easily. And directly questions like this have been asked. Directly questions like this have been asked. I'm telling you. Okay? Perfect? Right, people? Am I clear to everyone? Am I clear to everyone, people? Quick. Quick. Now some scientist has come in the chats. Wrong formula. Okay, fine. Yeah. Perfect, guys. Am I clear? Am I clear? Am I clear? Am I clear, people? In the chats, quick. Yeah? Sir, it is not Z. What is it? X or Y? What is it? X or Y? Yeah? Is it X or Y? Is it X or Y? I'm asking you. Guys, this is not the atomic number here. Okay? This is not the atomic number. These are the moles of atoms of element present in 1 mole compound. Like for carbon, Z value is 6 here. For hydrogen, Z value is 12 here. For oxygen, Z value is again 6 here. I believe I'm super clear till here. Okay? All right. Let's move on then. Let's move on. Let's move on. Let's move on. Okay, for example, I'm writing a compound CH4. Okay, CH4. If I ask you what is the percentage, mass percentage of carbon in CH4, what is the molar mass of carbon? 12. How many moles of carbon do you see? 1 divided by. What is the molar mass of CH4? 16 multiplied by 100. This will give you the mass percentage of carbon. All right, this will give you the mass percentage of carbon. Now, like this, your mass percentage of your different elements is calculated in a compound. Now, my dear students, again, one of the most important topics from which question almost every year is asked. Every year almost. Okay? Question almost every year is asked. So have a look how the questions are solved based on your empirical and molecular formula. This is something very, very important. I don't know what's wrong here. Yes, it's a wound and it's irritating me. It is irritating me. Okay. See guys, understand. For example, if I talk about glucose, do you know any formula for glucose? Do you know any formula of glucose? Do you know any formula of glucose? One of the formula you would have heard, C6H12O6, right? Perfect. Now tell me one thing. What is the ratio of these atoms here? 6:12:6. This is the ratio. My dear students, can you further simplify this ratio? Yes, we can further simplify it. How? Divide throughout by 6. When I divide throughout by 6, 6 by 6 is 1, 12 by 6 is 2, 6 by 6 is 1. So we have got 2 ratios here. This ratio I'm calling as the actual ratio. This is the actual ratio. This is the simplest whole number ratio. This is the simplest whole number ratio. As per the actual ratio, the formula is C6H12O6. As per the simplest whole number ratio, the formula should be C1H2O1. That particular formula, which gives me the simplest whole number ratio, that is what you call as the empirical formula. And that formula which gives me the actual ratio, that's what you call as molecular formula. Point number 1. Okay, point number 1. My dear students, from the molecular formula, we can calculate molecular mass. From the molecular formula, we can calculate molecular mass. From the empirical formula, we can calculate empirical mass. Now, talking about glucose. What is the molecular mass of glucose? Use the molecular formula. It is carbon 12 multiplied by 6 plus hydrogen 1 multiplied by 12, oxygen 16 multiplied by 6. The value comes out to be 180 U. So what is this 180 U? It is the molecular mass of glucose. It is the molecular mass of glucose. Okay. What about empirical mass of glucose? Carbon, it's 12. How many carbon? 1. Hydrogen, it's 1. How many hydrogens? 2. Oxygen, it's 16. How many oxygen? 1. The value comes out to be 30 U. What is 30 U here? 30 U is the empirical mass. One is molecular mass, one is empirical mass. My dear students, once you get the molecular mass and empirical mass, then you are going to get a number. The number is X. What is X? X is the ratio of molecular mass to that of empirical mass of the substance. X is the ratio of molecular mass to that of empirical mass of the substance. And do remember, your molecular formula is nothing but empirical formula multiplied by this X. Your molecular formula is nothing but empirical formula multiplied by this X. Remember all these points. I'll be utilizing all these points in the questions. At the same time, do remember one more thing. Your molecular mass is nothing but 2 times the vapor density. Sometimes in the question, you'll be given with vapor density. You just have to multiply that with 2. You'll be getting the molecular mass. You will be getting the molecular mass. Okay? You'll be getting the molecular mass. Now, let's utilize all of these things in the question so that you get to know what we are doing exactly. Have a look, people. Have a look. Have a look directly what I'm saying. My dear students, you have got a compound that contains potassium, chromium, oxygen. You have got a compound that contains potassium, chromium, oxygen. As per the question, I'm given with mass percentage of these elements. As per the question, I'm given with mass percentage of these elements. Remember, first of all, either in the question you will be given with mass percentage, or you will be directly given with the masses of these elements, or you will be given with the mass ratio of these elements. These are the 3 things which can be given to you in the question. Either mass percentage of elements, or masses of the elements, or the mass ratio of the elements. My dear students, the first thing which you are supposed to do, what is that? Divide the given mass percentage, or divide the given mass with the atomic mass of the element. Atomic mass of potassium is 39. So 26 divided by 39. 35.4 divided by its atomic mass, that's 52. 38.1 divided by its atomic mass, that is 2.38. I got some values here. This is something which I call as atomic ratio. So the first and the most important thing, what is that? You are supposed to calculate atomic ratio. How do you get the atomic ratio? Given mass percentage of element divided by atomic mass of element. Given mass percentage of an element divided by atomic mass of an element. Right? I got the mass percent. I got the atomic ratio. Now, which one is the least number among these 3 values? 0.68. Divide all these numbers by the least number. So 0.68 by 0.68. 0.68 by 0.68. 2.38 by 0.68. What do I get? I got the least atomic ratio. The least atomic ratio of potassium, chromium, and oxygen is coming out to be 1:1:3.5. But is this the simplest ratio? This is not the simplest ratio yet. Convert this into the simplest whole number ratio. How do you convert this into simplest whole number ratio? This is not the whole number ratio yet. This is 3.5, right? So I'll be multiplying throughout by 2. This becomes 2:2:7. Now this is the simplest whole number ratio. And as per the simplest whole number ratio, the formula has to be K2Cr2O7. And that formula, which gives me the simplest whole number ratio, that is something which I call as the empirical formula. Okay? I'll show you one more question with that things will be clear. My dear students, look at this particular question. The question is, a compound of nitrogen and oxygen was found to contain 7:16 by mass of nitrogen oxygen. So mass ratio is given 7:16. Mass ratio is given 7:16. I told you in the beginning, either mass percentage will be given, or mass ratio will be given, or directly masses will be given. Okay, so in this question, mass ratio is given. What is the first thing I do? I'll be getting the atomic ratio. So 7 divided by atomic mass of nitrogen, 16 divided by atomic mass of oxygen. This is 0.5. This is 1. Which one is the least term among the two? 0.5. Divide both these terms by the least ones. You'll be getting the least atomic ratio. So 0.5 divided by 0.5 is equal to 1. 1 divided by 0.5 is equal to 2. So the least ratio between nitrogen and oxygen I got as 1:2. Perfect. Which is the simplest whole number ratio. If it is the simplest whole number ratio, so what has to be the empirical formula then? Empirical formula has to be N1O2. This is the empirical formula. So you got the empirical formula. Am I supposed to calculate the empirical formula? No. I'm supposed to calculate the molecular formula. And you know, molecular formula is nothing but it is empirical formula multiplied by x. Empirical formula I have calculated N1O2. Now we have to get the value of x. We have to get the value of x. How do I get the value of x? X is nothing but it is molecular mass of the substance divided by the empirical mass of the substance. What is the molecular mass of the substance? Vapor density is given. And you know molecular mass is equal to twice vapor density. So 46 into 2 is 92 divided by empirical mass. Use the empirical formula and calculate empirical mass. 14 into 1 plus 16 multiplied by 2. The value comes out to be 46. So this 46U is the empirical mass. The value comes out to be 2. The value comes out to be 2. If the x value is equal to 2, that means your molecular formula is something like this. N2O4. This is something which I was supposed to calculate in the question. So with this, our first chapter is done and dusted. And my dear students, expect these sort of questions in your examination. Okay? Expect the similar sort of questions in your examination. Right? So let's take a break here. Dinner break. But only at one cost. I would want every one of you to be back. I would want every one of you to be back. Are you going to do that? Chirusha, that is not important. Don't worry. Is it a promise? You're supposed to be back on time, guys. Otherwise, there's no fun in teaching, okay? If you guys are not coming, then I'll be ending the session. There's no fun then. Okay? Yeah? All right. So the break is still, it is 9:46 right now. So the break is still 10:20. Okay, since it's a dinner break, that's why I'm giving you the break for 24 minutes. Sorry, 34 minutes, 33 minutes. Yeah? Okay? But be back on time. Be back on time. Have your dinner. Okay? Or if you want to have some tea or coffee, you can have it. But be back on time. I'll be waiting for all of you. I will be waiting for all of you. Perfect? See you after the break, people. Take care. See you after the break. All right. So are you guys back? Are you guys back? Or you guys have slept? Are you guys back? People, quickly, quickly, quickly in the chats. Quickly in the chats. Let me see your chats. All right. All right. Back with the same energy. Okay. Okay. All right. So tell me one thing, guys. Which chapter do you want the next? I'm giving you options. Atomic structure or redox? Tell me quickly. Atomic structure or redox? Tell me quickly. Tell me quickly. Atomic or redox? Uh, so it's a mixed response. Wait, I'll create a poll. I'll create a poll. Through the poll, tell me. Just a second, just a second. Just a second, guys. Start a poll. Next chapter. Atomic redox. All right, now tell me. I've created a poll, so let me know in the chats quick. Atomic redox. So majority is saying atomic structure, huh? Okay, majority is saying atomic structure. So let's go with the atomic structure then, huh? Let's go with the atomic structure. Let's go with the atomic structure then. All right, got it. Got it, people. Should we start? All ready again? All ready again? All ready again? Need some fire in the chats to begin one more amazing chapter? And the easiest one. It is the easy chapter, you know it. Perfect, perfect. All right, guys. Let's get going with the chapter Atomic Structure. My dear students, the first topic which we are going to cover here, that is your Planck's quantum theory. See, one thing I'm telling you. In your atomic structure, there is a topic called as discovery of electron, discovery of proton, discovery of neutron. That is never asked in your exam. That will never be asked in the exam. So don't waste your time in that. Okay? We'll directly get going with the first topic from which the question is asked. That's your Planck's quantum theory. Now, what this Planck's quantum theory tells us. My dear students, you must be knowing, as per your Planck's quantum theory is concerned, as per your Planck's quantum theory is concerned, energy is transmitted, energy is, or wait, I think I have already mentioned this over here. Okay, have a look. Have a look, people. As per Planck's quantum theory is concerned, energy is transmitted in the form of small packets. Energy is transmitted in the form of small packets or units. And you call those units, you call those small packets as what? You call those small packets as quanta. You call those small packets as quanta. For example, let's say this is the source of energy, for example. Let's say this is the source of energy, right? Which is emitting energy, basically. Which is emitting energy. Okay? Which is emitting energy. My dear students, this source of energy, which is emitting energy, right? It consists of small packets or units. It consists of small packets or units. And these small packets are what you call as, one small packet is what you call as quantum, and a lot of packets are what you call as quanta. Perfect. So first of all, energy is transmitted in the form of small packets or units, and those units are called as quanta, basically. In case of light energy, let's say this is the source of light energy. In case of light energy, these quantas are called as photons. These quantas are called as photons. And photons are going to travel with the speed of light when it comes to vacuum. Now comes a point. Energy carried by one photon. Energy associated with one photon. Energy associated with one photon. E is always equal to h nu. Energy associated with one photon is nothing but h nu. Or you can say it is equal to hc divided by lambda. Energy associated with one photon, okay, is equal to E is equal to h nu, or you can call it as hc divided by lambda. If the energy associated with one photon is h nu, therefore I must say energy associated with n photons. Energy associated with n photons would be equal to n times h nu, or you can say it is equal to n times hc divided by lambda. Energy associated with n photons is equal to n times hc divided by lambda. Okay, n times hc divided by lambda. My dear students, let me tell you, what is the SI unit of energy? SI unit of energy. SI unit of energy, you must be knowing, that is joule. SI unit of energy is joule. And in this chapter, we are going to use one more unit of energy. In this chapter, we are going to use one more unit of energy. What is that? That is electron volt. That is electron volt. And remember, my dear students, 1 electron volt is nothing but 1.6 into 10 raised power minus 19 joules. 1 electron volt is nothing but 1.6 into 10 raised power minus 19 joules. At the same time, my dear students, remember one thing. The value of H multiplied by C, the combined value of H multiplied by C, you are going to take as 12400 electron volt angstrom. The combined value of H multiplied by C, you guys are going to take 12400 electron volt angstrom when lambda is taken in angstroms. When lambda is taken in angstroms. Similarly, the value of H multiplied by C, you guys are going to take as 1240 electron volt nanometer when lambda is taken in nanometers. When lambda is taken in nanometers. These are the two things which I would want every one of you to remember. These are the two things which I would want every one of you to remember, my dear students. Okay? And people, if you remember just these two things, we are ready to solve a question. We are ready to solve a question on this. Before solving the question, do remember the value of Planck's constant as well, 6.6 into 10 raised power minus 34. Okay? Now, my dear students, look at this particular question. Look at this particular question. One simple and basic question this is. The question says, calculate the energy of 100 photons. Calculate the energy of 100 photons. If the wavelength of light is 2000 angstroms, energy carried by 100 photons will be equal to or energy carried by n photons is equal to n times hc divided by lambda. Now n value is 100. N represents number of photons. Since lambda is in angstroms, so h multiplied by c I'll take as 12400 electron volt angstrom divided by lambda is equal to 2000 angstroms. So angstrom gets cancelled out, right? This double zero cancels out. This zero cancelled out. The value comes out to be 620 electron volts, right? This is the energy carried by how many photons? This is the energy carried by 100 photons, people. This is the energy carried by 100 photons in what? In electron volts. Now, if they ask you to calculate energy in joules, then you know 620 multiplied by 1 electron volt is nothing but 1.6 into 10 raised power minus 19. Then the answer is going to be in joules. Perfect. Depending on what your options are, whether the options are in electron volts or the options are in joules. I hope this particular question is clear to everyone. Okay. My dear students, one more thing. My dear students, one more thing. One more thing. One more thing. I believe this particular question is clear to everyone. One more thing. One more topic from which question comes. Okay. I'm going to give its description in a short and precise way. That is photoelectric effect. Okay. That is photoelectric effect. What this photoelectric effect is all about. First of all, let me tell you this photoelectric effect, it supports which nature of light? It supports particle nature of light. Okay, you know light has got dual nature. Light has got dual nature. Some of its phenomenon are explained by considering light as the wave, and some of its phenomenon are explained by considering light as the particle. You know that already, right? Remember this photoelectric effect, it supports which nature of light? It supports the particle nature of light. Now, my dear students, when light is incident on a certain metal, electrons are emitted by the metal. Electrons are emitted by the metal. And those emitted electrons are called as photoelectrons. Those emitted electrons are called as photoelectrons. The current that flows due to the motion of these photoelectrons is called as photoelectric current. And this phenomenon overall is called as photoelectric effect. Now, let me tell you what exactly it means. My dear students, imagine this is your metal surface. If this is the metal surface, now on this metal surface, there will be positively charged ions. And in between these positively charged ions, there are electrons as well. In between these positively charged ions, there are electrons as well. Now, my dear students, if you select one of the electron, let's say I'm selecting this electron. This is the electron. Can I say this electron is attracted by this positively charged ion, this one as well, this one as well. So this electron is bounded right now. This electron is bounded right now. My dear students, in order to, first of all, if you talk about this electron, right? This electron is attracted by this ion, this ion, this ion, right? So there's a force of attraction here. There's a force of attraction between the electron and the ions. In order to break that force of attraction, you have to supply energy. And you are supplying energy in the form of what? You are supplying energy in the form of light. Now, when the light will be striking this electron, the force of attraction between the ions and electron will break down. When that force of attraction breaks down, this electron will come out. And the electron that comes out, that's what you call as photoelectron. And this overall phenomenon is what you call as photoelectric effect. Okay. My dear students, only one thing which you have to remember here. What is that? Understand what that means. For example, imagine that the incident light, the incident energy is equal to 100 joules. Imagine that the incident energy is 100 joules. For example, in order to take the electron out, let's say 80 joules of energy is required. Let's say minimum 80 joules of energy is required to take the electron out. How much I'm supplying? I'm supplying 100 joules. Out of 100, how much is required to take the electron out? 80 joules. How much is left? 20 joules is left. This 20 joules of energy will be imparted to the electron in the form of its maximum kinetic energy. So basically, the point is the incident energy is used for two things. One, to break the force of attraction. Okay. Number two, to give the maximum kinetic energy to the electron. So I'll simply say your incident energy is nothing but it is equal to your work function plus maximum kinetic energy imparted to the electron. Okay. What is this work function? It is the minimum amount of energy required to knock out the electron. Simple. Minimum amount of energy required to knock out the electron. Perfect. The minimum amount of energy required to knock out the electron is called as threshold, is called as work function. The minimum amount of energy required to knock out the electron from the surface is what you call as the minimum amount of energy required to knock out the electron. Okay, that's something which you call as work function. Perfect. Right? Now, my dear students, your work function is nothing but it is equal to h nu naught. It is equal to h nu naught. What is this nu naught called? This is called as threshold frequency. This is called as threshold frequency. So what is threshold frequency? It is the minimum frequency required to knock out the electron. In simple words, minimum frequency required to knock out the electron. Now, my dear students, this particular equation is important from which questions are asked. Incident energy is equal to h nu. Work function is equal to h nu naught. Ke max is equal to half of mass of electron multiplied by velocity of electron square. This is one equation from which questions are asked. Or you can make this equation in a different format. You can write hc divided by lambda is equal to hc divided by lambda naught plus your half of me ve square. Right? You can make this equation in this format as well. You can make this equation in this format as well. My dear students, what is the condition? What is the condition? What is the condition for photoelectric effect to happen? My dear students, energy of the incident radiation. That means incident energy. Incident energy should be greater or equal to work function. Incident energy should be greater or equal to work function. Then only your photoelectric effect will happen. Then only the electron will come out. Then only the electron will come out. Incident energy, you know, is equal to h nu. Okay. Work function is equal to h nu naught. So when h gets cancelled, I'll say nu has to be equal to nu naught. Nu has to be equal to nu naught. So I can say, my dear students, I can say the frequency of the incident light, should be greater or equal to the threshold frequency. The frequency of the incident light should be greater or equal to threshold frequency. Then only your photoelectric effect will happen. So this is one of the condition, or you can say this is your condition for the photoelectric effect to happen. Now at the same time, what is nu? Nu is equal to c by lambda. What is nu naught? C divided by lambda naught. C gets cancelled out. So lambda has to be less or equal to lambda naught. Lambda has to be less or equal to lambda naught. Okay. The wavelength of the incident light should be less or equal to threshold wavelength. Wavelength of the incident light should be less or equal to threshold wavelength. Perfect. Then only photoelectric effect is going to happen. If I'm clear, let me know once in the chats. Do remember these three conditions. These are the three conditions to be followed. Then only your photoelectric effect is going to happen. Quickly, my dear students. Energy of the incident light should be greater or equal to threshold energy. Okay. Similarly, the wavelength of the incident light should be greater or equal to threshold wavelength. Sorry. Your frequency of the incident light should be greater or equal to threshold frequency. And the wavelength of the incident light should be less or equal to threshold wavelength. Perfect. So this is the condition which has to be followed. Then only photoelectric effect is going to happen. I believe I'm clear with this. I believe I'm clear with this. Okay. I believe I'm clear with this. Let's try to solve one question with the help of which you'll understand what the question is all about. See guys. The question is, have a look properly. If the work function of the metal, phi naught, is equal to 3.1 electron volt. Work function is equal to 3.1 electron volt. Find its threshold wavelength, maximum kinetic energy emitted when the radiation of 300 nanometers strikes the metal. Okay, when the radiation of 300 nanometers strikes the metal. So lambda is given to me as 300. Lambda is given to me as 300. So if lambda is given to me as 300, I'll say incident energy is equal to hc divided by lambda. Lambda is equal to 300. So hc value has to be equal to 1240 electron volt nanometer divided by lambda. Lambda is nothing but that is 300 nanometer. So this term cancels out. So how much this value comes out to be? 3431. So 4.1 electron volt. Okay. So this is the incident energy. This is the incident energy. If this is the incident energy, this is the work function. I told you a few minutes back, incident energy is equal to work function plus maximum kinetic energy imparted to the electron. So from this particular equation, you can calculate Ke max. And Ke max is equal to Ei minus phi naught. What is Ei? Ei is 4.1. What is phi naught? That is 3.1. The value comes out to be 1 electron volt. This is the maximum kinetic energy imparted to the electron. Okay? Right? At the same time, what am I supposed to calculate? I'm supposed to calculate threshold wavelength as well. You know, your phi naught value is given to me as 3.1. Right? Phi naught is nothing but hc divided by lambda naught. So hc divided by lambda naught is equal to 3.1, which means that your lambda naught has to be equal to hc divided by 3.1. hc value is equal to what? hc value is equal to 1240 electron volt nanometer divided by what? Divided by 3.1 electron volts. Perfect. So this electron volt cancels out. Solve it and get the threshold wavelength from here. Am I clear? Am I clear, people? Quickly let me know in the chats. So like this, your questions are asked from your photoelectric effect. Yeah? Am I clear, my dear students? Am I clear? Am I clear? Let me know quickly in the chats. And if I'm clear, let me know the answer of this question. Look at the question carefully and let me know its answer quickly. Let me know its answer quickly. What do you think about this? The work function of some metals is given. All right. The number of metals which will show photoelectric effect when light of 300 nanometer falls on the metals. So first of all, let's calculate the incident energy. Incident energy is equal to hc divided by lambda. Okay, hc divided by lambda. Lambda is equal to 300. So hc has to be equal to 1240 electron volt nanometer divided by lambda is equal to 300. Lambda is equal to 300 nanometers, right? So how much this value comes out to be? This value comes out to be again 4.1 electron volt, right? So incident energy is 4.1 electron volt. What is the condition for photoelectric effect to happen? I told you a few minutes back. Incident energy has to be greater or equal to phi naught. How much is incident energy? 4.1. What is phi naught here? 2.1. So incident energy is greater than phi naught. 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 Here it is not. Here it's not. Here it's not. So how many metals will show photoelectric effect? Quick. How many metals will show photoelectric effect? I'll say these are the 4 metals here which are going to show the photoelectric effect. Because in these 4 metals, if you see carefully, incident energy is greater than your phi naught. Okay? Am I clear, people? Am I clear? Am I clear? Quickly. Yeah? Am I clear? Perfect. All right, guys. My dear students, the next thing is, what is the next thing here? The next thing is your application of Bohr's theory. Application of Bohr's theory. That is also important, right? Application of Bohr's theory, which is asked in our exam. Application of Bohr's theory. That's asked in our exam. Okay, questions are asked from that. The first application is to calculate the radius of nth Bohr's orbit. to calculate the radius of nth Bohr's orbit. To calculate the radius of nth Bohr's orbit, which I'm representing simply with Rn. Rn. What does it mean, first of all? For example, I have got the atom. This is the nucleus of the atom, right? Let's say this is the electron. This is the electron, which is revolving in some nth shell. It can be 1, 2, 3, or whatever. It is revolving in the nth shell. Perfect. Let's say atomic number of the atom is Z. Okay, atomic number of the atom is Z. I need to calculate the distance from the center of nucleus till here. I need to calculate this particular distance, which I'm calling as the radius of nth Bohr's orbit. How do you calculate the radius of nth Bohr's orbit? There is a simple formula for that. Radius of nth Bohr's orbit is nothing but R naught n square divided by Z. R naught n square divided by Z. Okay. And the value of R naught is how much? 0.529 angstroms. 0.529 angstroms. N represents the shell number in which electron is revolving. Z represents the atomic number. Z represents the atomic number. Okay. Z represents the atomic number. Now, my dear students, imagine that we have got two atoms. Imagine that we have got two atoms. This is one more atom. This is one more atom. This is one more atom whose atomic number is, for example, Z. Let's say this electron is revolving in shell number N1. Let's say this is the atom whose atomic number is Z2 and the electron is revolving in shell number N2. For example, I need to compare the radius of these two Bohr's orbits. This I'm representing with R1. This radius I'm representing with R2. This radius I'm representing with R2. Okay. This radius I'm representing with R2. Let's say I have to compare these two radii. So what I'll be doing? I'll be writing simply R1 divided by R2 is equal N1 square divided by N2 square multiplied by Z2 divided by Z1. This is how you compare the radii of two Bohr's orbits of two different atoms. Okay. This is how you compare the radii of two Bohr's orbits of two different atoms. This is the first application of your Bohr's theory. Its question I'll be solving in some time. First of all, we need to know more of its applications. We need to know more of its applications. We need to know more of its applications. The second application of this Bohr's theory, what is that? Calculation of velocity. Calculation of velocity of the electron, again, in the nth Bohr's orbit. In the nth Bohr's orbit. Okay. How do we calculate the velocity of the electron in the nth Bohr's orbit? Velocity of electron in the nth Bohr's orbit. Let me tell you, velocity of the electron in the nth Bohr's orbit is nothing but it is V naught Z divided by N. It is V naught Z divided by N. What is V naught exactly? V naught value is equal to 2.18 into 10 raised power 6 meter per second. This is the value of V naught. Again, my dear students, if you need to compare the velocities of two electrons moving in two different Bohr's orbits of two different atoms, how do you do it? You'll be writing simply V1 divided by V2 is equal Z1 divided by Z2 multiplied by N2 divided by N1. N2 divided by N1. Okay? N2 divided by N1. Right? Similarly, my dear students, the third application. What is that? How do we calculate the time period? How do we calculate the time period of the electron in the nth Bohr's orbit? In the nth Bohr's orbit. In the nth Bohr's orbit. I'm representing it with Tn. I'm representing it with Tn. Okay? I'm representing it with Tn. So time period of the electron in the nth Bohr's orbit is nothing but it is T naught n cube upon Z square. T naught n cube upon Z square. And when you need to compare the time periods, how do you do it? T1 divided by T2 will be equal to N1 cube divided by N2 cube multiplied by Z2 square divided by Z1 square. This is one more important application from which the question is asked. Let me know once in the chats if I'm clear. Quickly. Quickly, my dear students. This is the value of T naught as well. This is the value of T naught as well. Okay. All right. Similarly, the fourth application is calculation of frequency. Calculation of frequency. Calculation of frequency of the electron moving in the nth Bohr's orbit. Calculation of frequency of the electron moving in the nth Bohr's orbit. You know your frequency. Frequency is inversely proportional to time period. Frequency is basically equal to 1 divided by t. Frequency is basically equal to 1 divided by t, right? 1 divided by time period, right? So my dear students, here, frequency of the electron in the nth Bohr's orbit, it will be directly proportional to what? If that was n cube by z square, this is going to be z square divided by n cube. This is going to be z square divided by n cube. Okay? And here you can compare the frequencies. Mu1 divided by mu2 is equal to z1 square divided by z2 square multiplied by n2 cube divided by n1 cube. Okay? Divided by n1 cube. Similarly, people, remember one more thing. Remember one more thing. Remember one more thing. What is that? That is total energy of the electron. Total energy of the electron in the nth Bohr's orbit. Total energy of the electron in the nth Bohr's orbit, which I'm representing with En. Total energy of the electron in the nth Bohr's orbit is nothing but minus 13.6 z square divided by n square electron volts. This is the total energy of the electron in the nth Bohr's orbit, right? If I talk about the kinetic energy of the electron in the nth Bohr's orbit, that is plus 13.6 z square divided by n square electron volts. If I talk about the potential energy in the nth Bohr's orbit, that's equal to minus 27.2 z square divided by n square electron volts. Remember these three results as well. Remember these three results as well. Okay? Remember these three results as well. Perfect? Perfect, guys? Perfect. Quickly in the chats. All right. If this is clear, if you remember these formulae, tell me the answer of this question. What do you think? Tell me the answer of this question quickly. What is going to be the answer of this question? What is going to be the answer of this question? Calculate the radius ratio of second orbit of He positive and third orbit of Be tri positive. So basically we are given with He positive and at the same time we are given with Be tri positive. Okay. First thing, my dear students, what is the atomic number? Let me call this as He positive as number 1. Let me call this as number 2. Just giving the numbering. Calling this as number 1, calling this as number 2. Now people, atomic number of helium, hydrogen, helium, that is 2. Atomic number of beryllium, hydrogen, helium, lithium, beryllium, that's 4. Okay. Second orbit of He positive. So N1 is 2. N1 is 2. Here they have mentioned third orbit of Be tri positive. So N2 is 3. Let the radius here is R1. Let the radius here is R2. What am I supposed to calculate? Calculate the radius ratio of this and this. So basically, I want to calculate the value of R1 divided by R2. Okay. And you know, our radius of nth Bohr's orbit is equal to R0 n square by Z. And it's going to be N1 square divided by N2 square. And this is going to be Z2 divided by Z1. This is the formula which I gave you a few minutes back only. So people, what is N1 square? N1 square, 2 ka square is 4. What is Z2? Z2 is 4 divided by, what is N2 square? That is 3 ka square, 9. Z1 is 2, right? So it's coming out to be 16 divided by 18. So 2, 8, 2, 9. So 8 is to 9 is the radius ratio of these two orbits which I was supposed to calculate. Am I clear to every one of you? Say it once in the chats. Say it once in the chats, people. Say it once in the chats quickly. Say it once in the chats quickly. Yeah? Perfect. All right. If you look at this question, can you solve this one? Can you solve this one on your own? Gunjan, no effect on charge. Can you try to solve this one? Look at the question carefully. Look at the question carefully. My dear students, as per the question is concerned, if the velocity of the electron in the first orbit of hydrogen is V, what will be the velocity of the electron in the third orbit of Li positive? Li positive. I'm calling this as number 1 for your convenience. I'm calling this as number 2, again for your convenience. Okay? Now, my dear students, as per the question, velocity of the electron in the first orbit of hydrogen atom is V. Since I'm talking about hydrogen, so its atomic number is 1. What will be the velocity of the electron in the third orbit? Okay, of Li positive, hydrogen, helium, lithium. So atomic number is again 3. Let its velocity, we have to calculate its velocity. V2 value we have to calculate. Few minutes back, I gave you one result. Velocity of the electron in the nth orbit is equal to V naught Z by N. V naught Z by N. So I can say V1 divided by V2 is equal to Z1 divided by Z2, and this is N2 divided by N1. Perfect. Now, my dear students, look carefully. What is V1? V1 value is V divided by V2 divided by V2 is equal to Z1 is 1. What is N2? N2 is 3. Z2 is 3. N1 is 1. So this got cancelled. So you got to know V2 is nothing but V2 is equal to V. V2 is equal to V. Yeah? Is this clear? So you got to know V2 is nothing but V2 is just equal to V. I hope this is also clear. I hope this is also clear. Right? I hope this is also clear. All right, guys. If I talk about your hydrogen atom, just a second, guys. There are some spammers which have come. I need to block them. Blocked. All right. Let's move on now. If I talk about which atom? If I talk about, for example, hydrogen atom, right? My dear students, imagine this is the ground state of hydrogen, N is equal to 1. Imagine this is the second shell of the hydrogen. This was ground state. N is equal to 2 is called as first excited state. N is equal to 3 is called as second excited state. N is equal to 4 I'll be calling as third excited state. Similarly, N is equal to 5 I'll be calling as fourth excited state, and so on. Okay. How do I calculate energy of the electron in the nth Bohr's orbit? It is equal to minus 13.6 Z square divided by N square electron volts. Now, in case of hydrogen, Z value is already 1. In case of hydrogen, Z value is already 1. Okay, Z value is already 1. Now, my dear students, when the electron is present in shell number 1, how much its energy will be? It will be minus 13.6. Z is 1, N is 1. So it is minus 13.6 electron volts. So energy of the electron in the first orbit, in the ground state of hydrogen is equal to how much? Minus 13.6 electron volts. Similarly, when you calculate for the second shell, it is minus 3.4 electron volts, minus 1.5 electron volts, minus 0.85 electron volts. energy of the electron in the infinite shell. Energy of the electron in the infinite shell. If n is equal to infinity, division by infinity comes out to be 0. So we can say energy of the electron in infinite energy shell, that is 0. Energy of the electron in the infinite energy shell is 0. Okay. Now people, if you try to understand carefully, energy of the electron in the first shell is minus, negative. Energy of the electron in the second shell, negative. Third shell, negative. Fourth shell, negative. And here it is 0. What does this negative sign first of all signify? This negative sign signifies that the electron is under the influence of the nucleus. Negative sign signifies that the electron is under the influence of the nucleus. Electron is under the influence of the nucleus. So here the energy is coming out to be negative. That means nucleus is attracting the electron here. Nucleus is attracting the electron here also. Nucleus is attracting the electron here also. Nucleus is attracting the electron here also. But here, I must say, when I say that the electron is present in the infinite energy shell, that means electron is out of the influence of the nucleus. Electron is out of the influence of the nucleus. Okay? So remember, the negative sign signifies that electron is under the influence of the nucleus. Okay? If I say electron is present at the infinite energy state, that means the electron is out of the influence of the nucleus. That means electron has been taken out of the atom. Right? My dear students, one more thing. What is the energy gap between first and second shell? Energy gap between first and second shell is coming out to be 10.2 electron volts. Energy gap between second and third is coming out to be 1.89. Similarly, third and fourth will be lesser than this. Fourth and fifth will be lesser than this. So remember, as the shell number increases, the energy gap between the successive shells, it keeps on decreasing. Energy gap between the successive shells, it keeps on what? It keeps on decreasing. Okay? Energy gap between the successive shells, it keeps on decreasing. Remember this particular point as well. Okay? Remember this particular point as well. One more important thing, my dear students. One more important thing. Remember that. My dear students, remember, let's say the electron is present here. For example, electron has to jump from shell number 1 to shell number 2. Let's say electron has to jump from shell number 1 to shell number 2. So that means the electron has to go from lower energy state to higher energy state. Whenever electron has to go from lower energy state to higher energy state, energy is absorbed by the electron. Energy is absorbed by the electron. How much energy is absorbed by the electron? Whatever is going to be the energy gap between these two shells. That much amount of energy will be absorbed by the electron. Then only the electron will go from shell number 1 to shell number 2. For example, electron has to go from shell number 1 to shell number 4, for example. Shell number 1 to shell number 4. Okay? Electron is going from lower energy state to higher energy state. Whenever electron goes from lower to higher, energy is absorbed by the electron. How much energy is absorbed by the electron? Whatever is going to be the energy gap between these two shells, same amount of energy will be absorbed by the electron. Then only it will go from 1 to 4. Okay? Similarly, if the electron has to come from 2 to 1, if the electron has to jump from 2 to 1, higher energy state to lower energy state. Remember, when the electron makes a transition from higher to lower, it emits energy in the form of radiation. When the electron makes a transition from higher energy state to lower energy state, it emits energy in the form of radiation. How much energy it emits? My dear students, if the electron is going from 2 to 1, whatever is the energy gap between these two shells, that much amount of energy is emitted by the electron in the form of what? In the form of radiation. I believe this is clear to everyone. If, my dear students, the electron has to go from 4 to 1, again the electron is coming from higher energy state to lower energy state. And when the electron makes a transition from higher to lower, again it emits energy. How much it emits? Whatever is going to be the energy gap between these two, that much amount of energy will be emitted by the electron. Okay? Am I clear till here? People? Quickly let me know in the chats. Quickly let me know in the chats. Quickly let me know in the chats. Yeah? Quickly let me know in the chats. All right. My dear students, now comes one of the important points. What is that? Have a look. When the electron makes a transition from lower energy state to higher energy state. When the electron makes a transition from lower energy state to higher energy state. At higher energy state, electron is unstable. When the electron is present at higher energy state. At higher energy state, electron is considered to be unstable. It just resides there for 10 raised power minus 8 seconds. It just resides there for 10 raised power minus 8 seconds and then jumps back. See, when the electron makes a transition from lower energy state to higher energy state, okay, at higher energy state, electron is considered to be unstable, right? It then jumps back. And when the electron jumps back, it emits energy. It emits energy. And my dear students, when the electron makes a transition from higher energy states to shell number 1, from higher energy states to shell number 1, we get a series of radiations. We get a series of radiations. Okay, we get a series of radiations, right? We get a series of radiations, which is what we call as Lyman series. When the electron makes a transition from higher energy state to shell number 1, it can be 4 to 1, 3 to 1, 2 to 1, right? The series of radiations which we get, the series of spectral lines which we get, you call this series as a Lyman series. Similarly, when the electron makes a transition from higher energy state to shell number 2, higher to shell number 2, higher to shell number 2, the series of radiations which we get, that's called as Balmer series. That's called as Balmer series. And when the electron makes a transition from higher energy state to shell number 3, from higher energy state to shell number 3, for example, from here to here, from here to here, from here to here, the series of radiation which we get is called as Austrian series. Austrian series. And when the electron makes a transition from higher energy state to shell number 4, the series of radiations which we get over here, that's called as bracket series, right? And when the electron makes a transition from higher energy state to shell number 5, from higher energy state to shell number 5, the series of radiations over here is what you call as Pfund series. Is what you call as Pfund series. Okay? This is something which is very simple, and I believe you already know this. So, when the electron makes a transition from higher energy state to shell number 1, series of radiations which we get, what do we call this as? You call it as Lyman series. Higher energy state to shell number 2, Balmer series. Higher energy states to shell number 3, Austrian series. Higher energy state to shell number 4, bracket series. Higher energy state to shell number 5, Pfund series. Right? Now, people, comes the most important point. What is that? What is that? That is calculation of wavelength. Calculation of wavelength lambda. For example, if the electron is making a transition from higher energy state to lower energy state, it emits radiation. It emits radiation. And my dear students, that radiation would be having some wavelength as well. How do we calculate that wavelength of the emitted radiation? How do we calculate a wavelength of that emitted radiation? That is given by Rydberg's formula. 1 by lambda is equal to R Z square, 1 upon N1 square minus 1 upon N2 square. This is the Rydberg's formula, which you guys will be remembering to calculate the wavelength emitted or absorbed during the transition. To calculate wavelength emitted or absorbed during the transition. Okay? My dear students, remember the value of 1 by R is equal to 911.5 angstroms. It is equal to, the value of 1 by R is equal to 911.5 angstroms. Now, here are few things which I would want to tell you. Have a look. The series of lines which we get here is called Lyman series. This is your Lyman series. This is Balmer, this is Paschen, this is bracket. My dear students, this particular line from 2 to 1, it is called as first line of Lyman. It's called as first line of Lyman. Or you can call it as H alpha line as well. This is called as second line of Lyman. You can call it as H beta line of Lyman as well. Similarly, H gamma line of Lyman, right? First line of Lyman means 2 to 1. Second line of Lyman means 3 to 1. Third line of Lyman means 4 to 1. Okay? Perfect. Similarly, first line of Balmer means 3 to 2. Second line of Balmer means 4 to 2. Third line of Balmer means 5 to 2. First line of Paschen means 4 to 3. Second line of Paschen means 5 to 3. Right? And so on. Perfect. And so on. Now, people, understand what I'll be saying now. For example, we are supposed to calculate the minimum wavelength emitted in Lyman. In case of Lyman series, what is the minimum wavelength emitted? What is the minimum wavelength emitted? Okay. What is the minimum wavelength emitted? How do we calculate this? How do we calculate this? My dear students, first of all, in case of Lyman series, for wavelength emitted to be minimum, you know delta E is inversely proportional to lambda. For lambda to be minimum, can I say delta E has to be maximum? For lambda to be minimum, energy gap has to be maximum. In case of Lyman series, which one is the maximum energy gap? The maximum energy gap is when the electron makes a transition from infinity to 1. When the electron makes a transition from infinity to 1. So, in order to calculate minimum wavelength, the transition has to be from infinity to shell number 1. Okay, in case of Lyman series. Perfect. Now, put the values here. I can say 1 divided by lambda minimum is equal to R Z square. Since I'm talking about hydrogen, so Z is 1. 1 upon N1 square minus 1 upon N2 square. 1 upon infinity is 0. So 1 divided by lambda minimum is equal to basically R. Or I can say lambda minimum is equal to 1 divided by R, which is nothing but 911.5 angstroms. So this is the minimum wavelength emitted in case of the Lyman series. This is the minimum wavelength emitted in case of Lyman series. If I asked you to calculate maximum wavelength emitted in Lyman series, lambda max in Lyman. Lambda max in Lyman. Lambda max in Lyman. Tell me one thing. In case of Lyman, for the lambda to be maximum, delta E has to be minimum. For the lambda to be maximum, delta E has to be minimum. Okay. And in case of Lyman, minimum delta E is when the transition is from 2 to 1. When the transition is from 2 to 1. I hope you are getting what I'm trying to say. When the transition is from 2 to 1. So, in order to get lambda max in Lyman, I believe the transition has to be from 2 to 1. Lower energy state is represented by N1. Higher energy state is represented by N2. So, you can say 1 divided by lambda max is equal to R. Z square is 1. 1 upon N1 square minus 1 upon N2 square. So, I can say 1 divided by lambda max is equal to R. This is 1 minus 1 upon 4. So, it is 1 upon lambda max is equal to R. So, this is 3 divided by 4. Take the reciprocal of this particular equation. When you take the reciprocal of this equation, I can say lambda max is nothing but 4 divided by 3 multiplied by 1 by R. So, it is 4 by 3 and 1 by R is nothing but 911.5 angstroms. So, solve this. This is the maximum wavelength emitted when it comes to which series? When it comes to the Lyman series. I hope I am clear. Similarly, you can calculate lambda minimum and lambda maximum for your Balmer series, Paschen series, etc., etc., right? Yeah? I hope this is clear. Now, you tell me one thing. If I want to calculate lambda minimum in Balmer, what has to be the transition? If I have to calculate lambda minimum in Balmer, what has to be the transition? You tell me. For lambda to be minimum, delta E has to be maximum. And in case of Balmer, when is delta E maximum? When the transition is from infinity to 2. Infinity to 2. Yeah? Perfect. I hope this is clear. I hope this is clear. So like this, you can solve this. And people, there is one more small topic which you need to know. What is that? That is calculation of maximum spectral lines. How do we calculate the maximum spectral lines when the electron makes a transition? How do we calculate the number of spectral lines? Number of spectral lines is equal to n2 minus n1 multiplied by n2 minus n1 plus 1 divided by 2. This is how you calculate the total number of spectral lines or larger number of atoms when the electron makes a transition, basically. What does it mean? Let's say you have got a question. The electron is making a transition from 5 to 1. The electron is going to make a transition from 5 to 1. How many spectral lines are to be emitted? Lower energy state is represented by N1. Higher energy state is represented by N2. So, maximum number of spectral lines is equal to N2 minus N1 multiplied by N2 minus N1 plus 1 divided by what? Divided by 2. So, it's going to be 5 4s are 20. 20 divided by 2 comes out to be 10. 20 divided by 2 comes out to be 10. So, in total, there will be 10 spectral lines obtained in this particular case. Remember one more thing. Number of spectral lines falling in a particular series. What does that mean? For example, if you are supposed to check out of these 10 spectral lines, how many spectral lines will fall in Lyman? How many spectral lines will fall into Balmer? How many spectral lines will fall into Paschen? It is always equal to N2 minus the ground state of that series. N2 minus ground state of that series. What does it mean? For example, out of these 10 spectral lines, let's say I have to check how many will fall into Lyman. It's going to be equal to N2 is 5 minus, what is the ground state of Lyman? That's 1. So out of 10 spectral lines, 4 will fall into Lyman. How many spectral lines will fall into Balmer? N2, that is 5 minus ground state of Balmer. So 5 minus 2 is 3. How many spectral lines will fall into Paschen? N2 minus ground state of Paschen, that is 3. The value comes out to be 2. Lyman, Balmer, Paschen. Then bracket. In case of bracket, how many spectral lines will be there? 1. If you do the addition of these, 4 plus 3 is 7, 7 plus 2 is 9, 9 plus 10 is 9 plus 1 is 10. So in total, there are 10 spectral lines, which we already know. Okay, so anything can be asked from this particular topic. I believe I'm clear to everyone. I believe I'm clear to everyone. Yes. Am I clear, people? Quickly, let me know in the chats if I'm clear. Yeah? So remember this particular topic as well. This is very, very, very important. From this particular table also question can be asked. If a question is asked, Lyman series falls into which category? Remember, Lyman series falls into ultraviolet category. Okay, ultraviolet category. Balmer series falls in which category? Visible region. Paschen series falls in infrared. Bracket series falls in infrared. Fund series, infra. This also infra. This is a memory-based question that can be asked. Okay, you can remember it like this: U, V, I, I. Okay, U is ultraviolet, visible, infra. Okay, perfect, guys. I hope I'm clear. I hope I'm clear with this. Yeah. All right. Now, my dear students, now I'm moving on to one more topic. What is that? I'll be skipping one topic here. I'll be skipping one topic. I won't be teaching one topic, but that is important. But that topic will be taught by Yavar sir in your next marathon. That is your de Broglie's hypothesis. Okay? Because that is your separate chapter in physics. Dual nature of matter and radiation. Perfect? So we have decided he will be teaching that particular topic. He will be teaching that particular topic in his marathon. Okay, so I'll be skipping that topic here. But that is important, I'm telling you. Right? That is the topic here. But in physics, that is a separate chapter. Okay? I'm moving on to one more topic here. What is it? It is Heisenberg's uncertainty principle. It is Heisenberg's uncertainty principle. My dear students, what this Heisenberg's uncertainty principle is all about? As per Heisenberg's uncertainty principle, it is, as per Heisenberg's uncertainty principle, the momentum and the position of a moving electron, the momentum and the position of the moving electron cannot be calculated simultaneously with 100% accuracy. The momentum and the position of the moving electron cannot be calculated simultaneously with 100% accuracy. If you try to calculate the momentum with 100% accuracy, there will be error in its position. If you want to check the position of the electron with 100% accuracy, there will be at the same time error in its momentum. So momentum and position of a moving electron cannot be calculated simultaneously with 100% accuracy. If you want to calculate momentum with 100% accuracy, at the same time there will be error in its position. If you want to locate the position of the electron with 100% accuracy, there will be error in its momentum. So both the things will not go hand in hand. So, my dear students, here I am representing few terms. One is delta x. Delta x is what I call as error or uncertainty. Error or uncertainty in position. Error or uncertainty in position. I am writing delta v. Delta v is what I call as error or uncertainty in velocity. Error or uncertainty in velocity, right? If you remember, what is P? P is momentum. Momentum is mass into velocity. If there is error in velocity, automatically there will be error in momentum. So delta P is nothing, which is m delta V. I'm calling it as the error in momentum. Error in momentum. You know your de Broglie's wavelength, lambda. Lambda is equal to h upon mv. Lambda is equal to h upon mv. If there is error in velocity, automatically there will be error in de Broglie's wavelength. So I'm writing one more term, delta lambda, which is what you call as error in de Broglie's wavelength, which is basically h upon m delta v. Okay, you call this as error or uncertainty in de Broglie's wavelength. In de Broglie's wavelength. Okay, in de Broglie's wavelength. Yeah, in de Broglie's wavelength. As per Heisenberg is concerned, these are the two equations which you have to remember. Error in the position multiplied by error in the momentum. It is found out to be greater or equal to h upon 4 pi. Now delta x, if I write as such, delta p is m delta v. Delta v I'm writing here, m I'm taking in the denominator. So you can write it like this as well. Delta x dot delta v is greater or equal to h upon 4 pi m. These are the two equations, my dear students, which you just have to remember. And from these two equations, questions can be asked. And what kind of questions can be asked? Let's get to know about that first. So remember these two equations. Delta x dot delta p is greater or equal to h upon 4 pi, right? Similarly, delta x dot delta v is greater or equal to h upon 4 pi m. h upon 4 pi m. For example, one simple question. One simple and basic question. This is the first type of question that can be asked. The question is, a particle has got the mass of 10 raised power minus 10 grams. Okay. Whenever a question is asked from Heisenberg's uncertainty, right? Remember, my dear students, we are going to take all the parameters as per SI system. So We have got 10 raised power minus 10 grams, which is basically 10 raised power minus 13 kilograms. Right? Perfect. 10 raised power minus 13 kilograms. So mass of the particle is 10 raised power minus 13. Velocity of the particle is 10 raised power minus 6, but centimeter per second. What do I need? I need it in meter per second. So it is going to be 10 raised power minus 8 meter per second. It is going to be 10 raised power minus 8 meter per second. Right? There is the uncertainty. There is the error in the velocity. So delta V is given to me as 0.001% of V. 0.001% of V. This is the error in the velocity. So I would say delta V is equal to, this is 0.001, 0.0001, sorry, 0.0001, which is 10 raised power minus 4%. 10 raised power minus 4% of what? Of V. V is 10 raised power minus 8. So this is 10 raised power minus 12 divided by 10 raised power 2. It comes out to be 10 raised power minus 10 meter per second. 10 raised power minus 10 or 10 raised power minus 12? It comes, sorry guys, there's a mistake, I think. If the velocity of the particle is 10 raised power minus 6 meter per second with 0.0001% uncertainty. Okay, calculated. No, it's correct. So this is going to be what? This is going to be 10 raised power 2 comes up, 10 raised power minus 2, so 10 raised power minus 14 meter per second. This is the error in the velocity. This is the error in the velocity. This is the error in the velocity. I hope you got to know how I take the error in the velocity. Now you have, what am I supposed to calculate? I'm supposed to calculate delta x. You know there is a formula, delta x dot delta v has to be greater or equal to h upon 4 pi m, right? I can say delta x has to be greater or equal to h upon 4 pi m multiplied by delta v. What is h? H is 6.6 into 10 raised power minus 34, right? Divided by 4. Pi value is 22 divided by 7. M is equal to 10 raised power minus 13, right? 10 raised power minus 13, right? 10 raised power minus 13. And your delta V came out to be 10 raised power minus 14. Solve this particular equation and get the answer exactly as per SI system. That means in meters. Yeah. So this is one of the types of the question that can be asked. Directly you have to put the values in the expression and get the answer. That's all. That's all, people. Am I clear? Am I clear? Am I clear with this? It is one easy question. You just have to put the values. That's it. You just have to put the values. That's it. You just have to put the values. That's it. Look at this question. This can be one more type of the question asked. And what is this? As per this question is concerned, my dear students, if the error in velocity and error in position are same, what will be the error in de Broglie wavelength? So delta lambda we have to calculate, which is basically h upon m delta v. Delta lambda we have to calculate, which is technically h upon m delta v. So basically I have to first of all get the value of delta v, put it here, right? How do I get the value of delta v? You know your delta v and delta x, they are equal. And if delta v and delta x are equal, we know delta v dot delta x is greater or equal to h upon 4 pi m, right? So it is going to be delta v ka square, because this and this are equal. So delta v ka square is greater or equal to h upon 4 pi m. Or I can say your delta v is greater or equal to under root of h upon 4 pi m. This is the value of your delta v. If you got the value of delta v, put it here. So I can say delta lambda is equal to h upon m. What is delta v? Delta v is under root of h upon 4 pi m. Perfect. Now a bit of calculation is needed. H I'm writing as such. Take this m inside the root. So it becomes h m square divided by 4 pi m. I've taken m inside the root. So one of the m gets cancelled. Take entire thing in the root. So it's going to be h square divided by h m divided by 4 pi. So h and h got cancelled. So it comes out to be finally under root of 4 pi h divided by m. This is basically your error in de Broglie's wavelength. This is the error in de Broglie's wavelength. And this is how you're supposed to solve this sort of a question. Yeah? Is this clear, people? Is this clear to everyone? Quickly in the chats. Is this clear to everyone? Quickly in the chats. Yeah? I hope every single thing is clear till here. Now, my dear students, look at this. What is it? Quantum numbers. My dear students, you must be knowing quantum numbers, these are basically the set of numbers. These are the set of numbers which gives us the complete information. The set of four different numbers. The set of four different numbers which gives us the complete information about the electron in an atom. Right? The set of four different numbers that gives us the complete information about an electron in an atom. About an electron in an atom. Remember, you have got four quantum numbers. One is your principal quantum number. One is azimuthal quantum number, represented by L. Magnetic quantum number, represented by M. Spin quantum number, represented by S. Out of these four quantum numbers, remember the first three quantum numbers. The first three quantum numbers, that is N, L, and M. The first three quantum numbers, they are the outcome of your Schrodinger's wave equation. The first three quantum numbers, this one, and this one, they are the outcome of your Schrodinger's wave equation. Now we have to talk about these quantum numbers one by one. My dear students, the first thing, this is pretty much simple. If you talk about your principal quantum number, let me tell you, principal quantum number is going to give us the idea about the shell number in which the electron is present. What do we normally say? Electrons are present in shells, but in the shells, there are subshells. In the subshells, there are orbitals. We say something like that, right? Principal quantum number is going to tell me that in which shell the electron is present, right? So first of all, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. N is equal to 1 represents your first shell, which is called as K shell. N is equal to 2 represents L shell. Similarly, this is your M shell, and this represents your N shell. So principal quantum number, it first of all gives me the idea whether the electron is present in first shell, second shell, third shell, or fourth shell, right? And this principal quantum number, it represents your size and energy of the shell as well. It represents your size and energy of the shell as well. Perfect? Right? That is the only thing which you have to remember about principal quantum number. It gives me the idea about the shell number in which electron is present. The shell number in which electron is present. At the same time, you know, as the value of n principal quantum number increases, size as well as energy of the shell increases. One more important point. And the maximum number of electrons that can be accommodated in a shell, the maximum number of electrons that can be accommodated in a shell is equal to 2n square. It is equal to n square. Is equal to 2n square. Now people, the actual one is, which is more important, that is azimuthal quantum number. It is more important. Okay? Azimuthal quantum number, it is going to give us the idea about the subshell in which electron is present. The subshell in which electron is present. The subshell in which electron is present. First of all, remember, the value of L is from 0 to n minus 1. Value of L is from 0 to n minus 1. And every value of L represents a subshell. Every value of L represents a subshell. If the value of L is coming out to be 0, that means we are talking about which subshell? S subshell. If the value of L is equal to 1, that means we are talking about your P subshell. We are talking about your P subshell. If the value of L is equal to 2, that means we are talking about the D subshell. If the value of L is equal to 3, that means we are talking about the F subshell. We are talking about the F subshell. Okay, every value of L represents a subshell. For example, talk about n is equal to 1. N is equal to 1 means first shell. If n is equal to 1, the value of L is going to be from 0 to n minus 1. 0 to 1 minus 1. 1 minus 1 is 0. That means L is only having one value. L is only having one value, that is 0. And every value of L represents a subshell. So in your first shell, there is only one subshell, which I'm calling as S subshell. For n is equal to 2. For n is equal to 2. How many values of L will be there? For n is equal to 2. 0 to 2 minus 1. That means L is having two values. 0 and L is having two values. 0 and 1. L is equal to 0 represents what? L is equal to 0 represents your S subshell. L is equal to 1 represents your P subshell. So in your second shell, there are two subshells, S subshell and P subshell. S subshell and P subshell. Similarly, if I talk about n is equal to 3, in case of n is equal to 3, L will have values from 0 to 3 minus 1. 3 minus 1 is 2, so 0 to 2. It is going to be either 0, it's going to be 0, 1 and 2. L is equal to 0 represents your S subshell. L is equal to 1 represents P subshell. L is equal to 2 represents D subshell. Similarly, for n is equal to 4, L is going to have values 0, 1, 2 and 3. This represents S subshell, this represents P subshell, this represents D subshell, and this represents F subshell. So basically, in case of your first shell, there is one subshell. In case of your second shell, there are two subshells. In case of your third shell, there are three subshells. In case of your fourth shell, there are four subshells, right? Okay. Every value of azimuthal quantum number represents a subshell. Okay. And my dear students, what all other things we have to remember here? This azimuthal quantum number, what is it used for? It is used to calculate orbital angular momentum as well. Which is equal to under root of L into L plus 1 h upon 2 pi. L into L plus 1 h upon 2 pi. A question is asked like this. For example, you have got 3s. In case of 3s, calculate the orbital angular momentum. Right? First of all, in case of S, the value of L is 0. If the value of L is 0, put the value of L as 0. So orbital angular momentum here is 0. For example, you have got 2p. What is the value of L for P? The value of L for P is 1. So you will be asked to calculate orbital angular momentum, which is under root of 1 into 1 plus 1. Under root of 1 into 1 plus 1, h upon 2 pi. So it is going to be root of 2 h upon 2 pi, or you can say it is nothing but h upon root 2 pi, right? Similarly, anything can be asked. For example, if they ask you to calculate the orbital angular momentum in case of 3D, for D, L value is 2. For D, L value is 2, right? If L value is 2, so orbital angular momentum has to be equal under root of L into L plus 1 h upon 2 pi. So 2 plus 1 is 3. So it's going to be root of 6 h upon 2 pi. So sometimes questions are asked from this orbital angular momentum as well. Okay. My dear students, the next quantum number is what you call as your magnetic quantum number. This is again important. Your magnetic quantum number, which I'm representing with M, whose value would be from minus L to plus L. See, principal quantum number gives me the idea about the shell number in which electron is present. Azimuthal quantum number gives me the idea about the subshell in which electron is present, right? And this magnetic quantum number is going to let me know in which orbital electron is present. It's going to give me the information about orbital in which electron is present. And remember, every value of M represents an orbital. Every value of L represents an orbital. Every value of M represents an orbital. For example, if L is equal to 0, if L, azimuthal quantum number, is equal to 0, that means we are talking about which subshell? We are talking about S subshell. Let's see how many orbitals are there in S subshell. If value of L is 0, m is going to be from minus 0 to plus 0. That means how many values of m I got? I got one value of m. I got one value of m, right? And every value of m represents an orbital, okay? And m is equal to 0. That means I got one value of m. That means in s subshell, there will be only one orbital, which I'm calling as s orbital directly. So in your s subshell, there is only one orbital, which I'm calling directly as s orbital. Which I'm calling directly as s orbital, right? Similarly, my dear students, if I talk about L is equal to 1, if I talk about L is equal to 1, L is equal to 1 represents your p subshell. It represents your p subshell. If the value of L is equal to 1, if the value of L is equal to 1, how many values of m are there? It's going to be minus 1 to plus 1. So minus 1, 0, plus 1. So how many values of m I got? How many values of m I got? I got 3 values of m. I got 3 values of m. And every value of m represents an orbital. So basically, in your p subshell, how many orbitals are there? There are 3 orbitals. In p subshell, there are 3 orbitals. One I'll be calling as px, one I'll be calling as py, one I'll be calling as pz. Okay? px, py, and pz. As simple as that. Similarly, for L is equal to 2, for L is equal to 2, L is equal to 2 represents your d subshell. For L is equal to 2, how many possible values of m will be there? Minus 2 to plus 2. Minus 2 to plus 2. So it's going to be minus 2, minus 1, 0, plus 1, and plus 2. So there are 5 values of m which I got. And every value of m represents an orbital. So basically, in case of your d subshell, how many orbitals will be there? There will be 5 d orbitals. There will be 5 orbitals. One of which is going to be dxy, then dyz, then dzx, one is going to be dx square minus y square, and one is going to be dz square. This is going to be the naming of these d orbitals. Okay? And similarly, my dear students, for L is equal to 3, you will have 7 orbitals. You will have 7 orbitals. Okay? You will have 7 orbitals. I believe I'm clear with this particular part as well. I believe I'm clear with this particular part as well. Am I? Is it clear? Is it clear? All right. Perfect. Perfect, guys. Now, the last quantum number is basically your spin quantum number. Last quantum number is basically your spin quantum number. And spin quantum number is simply going to tell you, whether the electron is going with clockwise spin or anti-clockwise spin. Spin quantum number is simply going to tell you that whether the electron is going with clockwise spin or anti-clockwise spin. If the electron is going with clockwise spin, the value of S is taken to be plus 1 by 2. If the electron is going with anti-clockwise spin, the value of S is going to be minus 1 by 2. The value of S is going to be minus 1 by 2. Okay? Perfect. Perfect, guys. Plus 1 by 2 means the electron is going with clockwise spin. Minus 1 by 2 means the electron is going with anti-clockwise spin. Now comes one of the most important topics, which you all must be knowing. What is that? That is shapes of orbitals. Shapes of orbitals. Shapes of orbitals. My dear students, if you talk about your s orbital, what is the shape of your s orbital? You should know s orbital is spherically symmetric, right? S orbital is spherical in shape. This, for example, nucleus, and this is the electron density around the nucleus. This is the electron density around the nucleus. This is how your s orbital looks like. It is spherically symmetric, right? It is spherically symmetric. If you talk about your p orbital, if you talk about your p orbitals, right? Your p orbitals. One is going to be pxy, sorry, one is going to be px, one is going to be py, and one is going to be pz. Okay, one is px, one is py, one is pz. Let me first of all tell you your p orbitals are dumbbell shaped. Your p orbitals are dumbbell shaped. And how exactly they look like? Have a look. See guys, for example, let me make it like this. For example, imagine this is your y-axis. Imagine this is your z-axis. So that means x-axis will be perpendicular to this. So this is your x-axis. Okay, this is your x-axis. P orbital, it's dumbbell shaped. In case of px, the lobes lie along the x-axis. The lobes lie along the x-axis, right? That means the electron density lies along the x-axis. You can see these two lobes. These lobes, they represent the electron density. So electron density is lying along the x-axis, right? These two lobes, they represent the electron density. Now, my dear students, do you see this particular plane? This particular plane is cutting the orbital in such a way that no electron density lies on it. On this plane, there is no electron density. On this plane, there is no electron density. So I'll be calling it as the nodal plane. So how many nodal planes are there in px? In px, there is one nodal plane. And what is the name of this nodal plane? It is your yz plane. It is your yz plane. It is your yz plane, right? It's your yz plane. Similarly, my dear students, if you talk about your py, in case of py, the lobes lie along y-axis. So again, there will be one nodal plane, and that's going to be xz plane. And here, again, there will be one nodal plane, that's going to be xy plane. That's going to be xy plane. I believe I'm clear with this. I believe I'm clear with this. Yes? Perfect. So this is how your p orbitals look like. Now, similarly, if you talk about your d orbitals, in case of your d orbitals, your first one is dxy, then you have got dyz, then you have got dzx, then you have got dx square minus y square, and at the end, you have got dz square, right? So d orbitals are first of all double dumbbell shaped. D orbitals are first of all double dumbbell shaped. See, for example, this is x-axis, this is y-axis, right? In case of dxy, the lobes lie between the axes. This is how your dxy looks like. If you talk about your dyz, this is y-axis, this is z-axis. The lobes lie between these axes. Okay. If you talk about your dzx, let's say this is x-axis, this is z-axis. The lobes lie between these two axes. If you talk about your dx square minus y square, let's say this is x, this is y. In case of dx square minus y square, the lobes lie along the axis. The lobes lie along the axis, right? In case of your dx square minus y square. In case of your dz square, let me show you how dz square looks like. Let me show you how dz square looks like. See guys, let's say this is your x-axis. Let's say this is your y-axis. So perpendicular to this, it's going to be your z-axis. How your dz square looks like, there'll be one lobe here. This is one of the lobe. There'll be one lobe here. This is one more lobe. Electron density. Okay, electron density. And my dear students, one more thing. On this plane also, there will be electron density. How exactly? It's going to be like this. on this plane also. On this plane also there will be electron density. So this is how your dz square looks like. Okay, one low electron density, and on this plane also there will be electron density. On this plane also there is electron density. Perfect. Remember, my dear students, if I talk about dxy, see, this particular plane and this particular plane, these are the two planes on which there is no electron density. So how many nodal planes are there? There are two nodal planes. One is going to be xz plane, one is going to be yz plane. Okay. Similarly, this is the plane and this is the plane. These are the two planes on which there is no electron density. So how many nodal planes? Two nodal planes. One is going to be xz and one is going to be yx. Perfect. Similarly, if you talk about your dzx, this is one nodal plane, this one nodal plane. Again, there are two nodal planes here also. One is going to be xy plane and one is going to be a yz plane. Right? Again here, this is one plane on which there is no electron density. One more plane on which there is no electron density. So how many nodal planes again? Two nodal planes. One is xz and one is yz. In case of dz square, there are two conical nodal surfaces. There are two conical nodal surfaces. In case of dz square, there are two conical nodal surfaces. This is one of the nodal surface. This is one of the conical nodal surface on which there is no electron density. This is one more conical nodal surface on which there is no electron density. Only one thing which you have to remember, in case of dz square, remember there will be two conical nodal surfaces, right? And right, on those conical nodal surfaces, there will be no electron density. Perfect. And my dear students, all these things you have to remember. All these things you have to remember. All these things you have to remember. Now comes one more important point. One more important point. What is that? That is calculation of nodes. Calculation of nodes. This is again an important topic from which question comes. My dear students, how do we calculate the total number of nodes? Total number of nodes are calculated by the formula n-1. Total number of nodes are calculated by the formula n-1. And these nodes are basically of two types. One is called as spherical, or you call it as the radial node. One is called as angular node. One is called as angular node. My dear students, let me tell you, angular nodes are given by the value of L. Radial nodes are given by the value of n minus L minus 1. N minus L minus 1. Okay? Okay? For example, let's say you have got 2p. You have got 2p. If I ask you how many total nodes are there, total nodes is equal to n minus 1. N is 2, so 2 minus 1 is equal to 1. So total node is 1. If I ask you how many angular nodes are there, angular node is equal to the value of L, and L value for p is nothing but 1. If I talk about the spherical node is n minus L minus 1. N is 2. N is 2, so 2 minus 1 minus 1. 2 minus 1 minus 1. The value comes out to be 0. Right? As simple as that. For example, you have got, let's say 3p. You have got 3p. What is the value of n first of all? N value is 3. What is the value of L for p? That's 1. So total number of nodes, n minus 1. So 3 minus 1 is 2. 3 minus 1 is 2. If I talk about the angular nodes is equal to the value of L. That's 1. If I talk about the spherical nodes is n minus L minus 1. The value comes out to be 1 exactly. The value comes out to be 1 exactly. So this is how you calculate the total nodes, spherical nodes, angular nodes. Now comes one more important thing. My dear students, in your syllabus, they have mentioned to draw the graph psi square versus R, and they have mentioned psi versus R for 1s and 2s only. For 1s and 2s only. This is mentioned in your syllabus. So you just have to know how to draw the graph between psi versus R and psi square versus R for 1s and 2s only. Okay? Let me show you how do we draw these two graphs. if I first of all talk about 1s, in case of 1s, the value of n is 1. What is the value of L for s? That is 0. So how many total number of nodes are there? N minus 1. So 1 minus 1 is 0. So there is no node. Perfect. The first graph is going to be psi versus r. The first graph is going to be psi versus r. And the second graph is going to be psi square versus r. Psi square versus r. The second graph is going to be psi square versus r. My dear students, one thing. Remember, whenever you are supposed to draw a graph between psi versus r or psi square versus r, in case of s orbitals, in case of which orbitals? S orbitals. They start from the top. They start from the top. Just remember it like this so that it will be easier for you. They start from the top. Okay? So it's going to start from the top and come down like this. But this graph is not going to touch this r-axis, because if it touches the r-axis, that point represents a radial node. But here, there is no radial node in case of 1s. Okay? Again, psi square versus r here is going to be the same. Now, for example, you have to, this was your 1s, right? So, let's try to draw it for 2s. Let's try to draw it for 2s. In case of 2s, the value of n is 2, the value of L is 0. So, total number of nodes is equal to n minus 1. 2 minus 1 is 1, right? 2 minus 1 is 1. So, there is only one node. There is one node, right? Which is basically the radial node. So, draw the graph. Draw psi versus r and psi square versus r. Psi square versus r. In case of s, these psi versus r and psi square versus r, they start from the top, right? They start from the top. Perfect. They start from the top and perfect. They start from the top. They'll come down, right? This particular point, it represents a node, a radial node. Okay. I had to represent one node and that node is this one. Now, when it comes to psi square versus r, just do one thing, just to make it easier for you. Just do one thing. Is there any part of the graph that is down the r-axis? Yes, this is the part of the graph which is down the r-axis. This is the part of the graph which is down the r-axis. Just remove it and take its reflection along this r-axis. So, from here to here, the graph is going to be same. Now, remove this part and take its reflection along this axis, right? So, it's going to be like this. This represents a radial node again. And this is psi square versus r for 2s. Only these two graphs are mentioned in your syllabus. Psi versus r and psi square versus r for 1s and 2s. Right? And my dear students, one more topic is left here in this particular chapter. What is that? That is your electronic configuration. And I believe electronic configuration, you all would be knowing already how to write. Do you know how to write the electronic configuration of different elements? Yeah? I think yes. Because this is something, guys, which is just tell me openly. Guys, electronic configuration. Do you know how to write for different elements? Don't tell me no, please. Don't say no. Of course, hydrogen 1s1, helium 1s2, 1s2, 2s2, 2p6, 3s, etc., etc. Right? I believe that's something which you already know. But only two things which you have to remember in case of electronic configuration, that is exceptional electronic configuration of chromium and copper. These two remember, right? The outermost configuration of chromium is 3d5, 4s1, and here it is 3d10, 4s1, right? Just remember these two configurations. Rest is the same. Rest is the same. Okay? Why chromium has this particular configuration? Why chromium has this particular configuration? Because of two reasons. One is symmetry. Symmetry leads to stability. And number two is due to more exchange energy. Same goes for your copper. Okay? And with this, your atomic structure is also done and dusted. With this, your atomic structure also done and dusted, people. All right. The next chapter is going to be your redox reaction, but let's take a break. Let's take a break till 12:30. Tell me first of all, are you guys going to be back on time? Are you going to be back on time? I know you don't need a break, but I need a break. Okay? I need a break. The whole day I had been in my offline center. So let me tell you honestly, today from 8 to 5, I have taken almost like 12 classes in my offline, right? Came back home at 5:30. Perfect. Then started your class at 8. Now it will go on. I don't know till what time. Then morning again at 8, I have to go for my offline. Okay. Then I'll be back at 5:30 tomorrow after taking again 12 classes. And after that, I can sleep. After that, I can sleep. After that, I can sleep. Yeah. So be back on time. Okay. Be back on time. I know it's difficult for you, but it's more difficult for me. Trust me. It's more difficult for me. So if I'm willing to stand here, you have to sit and listen to. Someone is saying I'm getting headache. I already have headache from past 2 hours. I never said it. Okay. So be back exactly at 12:30. At 12:30, I'll be starting the new chapter. All right. See you. Bye bye. All right, people, is everyone back? Is everyone back? Yeah? Tell me quickly in the chats. Is everyone back? All right, all right. What's up? How are you all? Sleepy or not? Sleepy or not? Let me check your chats here. Let me check your chats here. Sleepy or not? Yeah? Oh, someone is saying my sleep is sleeping, huh? Your sleep is sleeping. Wow. Okay, tell me one thing. Whatever things we discussed till now, is every single thing clear? Tell me in the chats. Whatever things we discussed till now, is every single thing clear? Yeah? Amazing. Let people join in again and we shall start. Let people join in and then we shall start. Someone wants me to shave my beard, huh? Okay. Yeah, I'll do that. Oh, no, there won't be questions asked from Schrodinger. Don't worry. There won't be questions asked from Schrodinger. There won't be questions asked from Schrodinger. Be relaxed. Be relaxed. All right then. So people, tell me once in the chats, have you studied redox reactions before? Have you studied redox reactions before this chapter? Tell me that in the chats quick. Just say it honestly, yes or no. Just say it honestly, yes or no. Okay. Got it. All right, people. Should we start then? Should we start? Say yes or no. Should we start? Say yes or no. All right, people. So let's get going then. Let's get started and finish off this chapter 2. That is your redox reaction. Okay. The chapter name is redox reaction. redox reaction. This is again one very important chapter. And my dear students, one thing I'm telling you, without this particular chapter, your electrochemistry chapter cannot be strong. Okay, you need to know that. So make sure this chapter is strong, then only your electrochemistry chapter automatically will turn out to be stronger. Yeah. The first topic which we are going to start here, that is going to be rules to calculate oxidation state. What are the rules by means of which we can calculate oxidation state of an element? Yeah, rules to calculate oxidation state. My dear students, the first rule, whenever you see an element present in its native state, whenever you see an element present in its native state, or I can say elemental state, its oxidation state is taken to be zero. For example, hydrogen in nature exists in the form of H2. Chlorine in nature exists in the form of Cl2. Nitrogen in nature exists in the form of N2. Iron exists as Fe solid. Copper exists as copper solid, right? So whenever you see an element present in its native state or elemental state, its oxidation state is taken to be zero. So oxidation state of all of these is equal to zero. Point number one. My dear students, point number two. Your group first elements, which are what you call as alkali metals. Let me tell you, the oxidation state of alkali metals is taken to be +1. Oxidation state of alkali metals, your lithium, sodium, potassium, rubidium, cesium, it is taken to be +1. And when you talk about the group second elements, that means I'm talking about your alkaline earth metals. Your alkaline earth metals, let me tell you, their oxidation state is taken to be +2. All right? These are the two things which you have to remember about group 1 and group 2 elements. Your group 1 elements show the oxidation state of +1. Your group 2 elements, they show the oxidation state of +2. Okay? Similarly, my dear students, if you talk about hydrogen separately, okay, hydrogen shows different oxidation states. First of all, when hydrogen is present in its native state, oxidation state of hydrogen is taken to be zero. But when the same hydrogen is attached with more electronegative element than itself, then oxidation state of hydrogen is taken as +1. And when the same hydrogen is attached with less electronegative element than itself, let me tell you, its oxidation state is taken as -1. For example, if you have got HCl, hydrogen is attached with more electronegative element than itself, so oxidation state of hydrogen is +1. For example, water, hydrogen is attached with more electronegative element than itself, its oxidation state is +1. If you talk about metal hydride, any metal hydride, for example, you have got sodium hydride. Okay, you have got, for example, MgH2. In all the metal hydrides, hydrogen is attached to less electronegative element. When hydrogen is attached to less electronegative element than itself, its oxidation state will be taken as -1. Okay, these are few things which you have to remember about hydrogen. Then comes one important one, that is your oxygen. My dear students, in case of oxygen, again you have to remember certain things. What are those certain things? Let's have a look. First of all, when oxygen is present in its native state, that means this particular form, the oxidation state of oxygen is taken as 0, number 1. When oxygen is attached to less electronegative element than itself, then remember, generally oxygen shows the oxidation state of -2. Oxygen shows the oxidation state of -2. For example, you have got water. For example, you have got MgO, right? Oxygen is attached to less electronegative element, so -2. Oxygen is attached to less electronegative element, then -2, right? Oxygen shows certain special compounds. Oxygen forms some special compounds which are what you call as peroxides. So what are peroxides first of all? Whenever you see in any compound, if there is oxygen single bond oxygen, in any compound, if there is oxygen single bond oxygen, this particular linkage is what you call as, peroxide linkage. This is what you call as peroxide linkage. And in case of peroxides, oxygen generally shows the oxidation state of -1. For example, if you talk about your hydrogen peroxide, H2O2, I hope you remember its structure. It is O single bond O. This is H and H. Over here, there is a single bond between two oxygen atoms. And whenever there is a single bond between two oxygen atoms, that means there is a peroxide linkage. There is a peroxide linkage. There is a peroxide linkage. And when there is a peroxide linkage, oxygen shows generally the oxidation state of what? -1. Okay? Perfect. Guys, just a second. There are some spammers coming. Wait. Mr. Pranav is blocked. Who else? Just a second. Okay, have a look now. Similarly, oxygen shows one more type of the compounds which you call as superoxides. And in case of superoxides, oxidation state of oxygen will be -1/2. For example, you have got KO2, potassium superoxide. You have got RbO2, rubidium superoxide. Whenever oxygen forms superoxides, its oxidation state will be taken as -1/2. Okay. My dear students, there is one more compound which oxygen shows. That's called as ozonide. And in case of ozonide, oxygen shows the oxidation state of -1/3. For example, you have got potassium ozonide, KO3, right? Oxidation state of oxygen here is simply going to be -1/3. Perfect. These are few things which you have to remember about oxygen. One more thing, people. Oxygen shows oxyfluorides as well. Oxygen forms oxyfluorides as well. That means oxygen forms two compounds here. One is OF2, one is O2F2. These are the two compounds wherein here oxygen shows +2 oxidation state and here oxygen shows +1 oxidation state. Remember these two compounds as well. Okay? These are few things which you have to remember about oxygen. Similarly, my dear students, there are few things which you have to remember about halogens as well. First of all, whenever you see halogen present in its native state, okay, oxidation state of halogen will be taken as 0, number 1. Number 2, whenever you see halogen attached with less electronegative element than itself. Whenever you see halogen attached with less electronegative element than itself, oxidation state of halogen is taken as -1. Oxidation state of halogen is taken to be -1. Okay? Right? Now, my dear students, whenever you see halogen attached with more electronegative element than itself, oxidation state of halogen can be positive. Right? For example, you have got Cl2O. In case of Cl2O, if you look at its structure, here halogen is chlorine. Between oxygen and chlorine, which one is more electronegative? Oxygen. So this bond pair will be shifted towards oxygen, due to which it gets -1 and it gets +1. Due to this bond also, this gets -1, this gets +1. So halogen here is showing what? It is showing +1 oxidation state. Right? It is showing +1 oxidation state. Yeah? And my dear students, at the same time, remember one more thing. There are a particular compound, there is a particular set of compounds which halogen forms, which are what you call as interhalogens. In case of interhalogens also, oxidation state of halogens is taken as positive. For example, you have got IF7. You have got BRF3. If I underline these elements, iodine and bromine, In case of IF7, iodine shows +7. In case of BRF3, bromine shows +3. So these are some special compounds wherein oxidation state of halogen will be taken as positive as well. Okay. So these are few things which you have to remember about halogens. Now, my dear students, at the same time, remember few more things. Remember the sum of oxidation states. The sum of oxidation states of all the elements. The sum of oxidation states of all the elements present in a molecule is always equal to the net charge present on the molecule. Is always equal to the net charge. What does exactly it mean, and how come this particular statement is going to be helpful? Try to understand what exactly I'll be saying. For example, I have got MnO4 negative. Okay. Let's say I have got Cr2O7 di negative. Right. Let's say I have got NH4 positive. NH4 positive. For example, I have got S4O6 di negative. S4O6 di negative. Right. S4O6 di negative. For example, I have got Br3O8. For example, I have got C3O2. C3O2. Right. For example, I have got Fe0.930. Fe0.930. The underlined elements, I need to calculate their oxidation states. How exactly am I going to do it? Let the oxidation state of manganese is equal to X. Okay. Oxygen generally shows -2 oxidation state. There are 4 oxygen atoms. Net charge is -1. Net charge is -1. When you get the value of X, X value will come out to be +7 after solving. Right? Pretty much simple. Let the oxidation state of chromium is X. There are 2 chromium atoms, so 2X. Oxygen shows -2. There are 7 oxygen atoms. Net charge is -2. When you solve it, the value of X comes out to be +6. So chromium here is in +6 oxidation state. Similarly, NH4 positive. Let the oxidation state of nitrogen is X. Hydrogen shows +1. There are 4 hydrogen atoms. Net charge is +1. So the oxidation state of nitrogen here will be -3. Talk about this sulfur. Let the oxidation state of sulfur is X. So it becomes 4X. Oxygen shows -2. There are 6 oxygen atoms. The net charge is -2. When you solve X, X value will come out to be +2.5. Similarly, the value of X will come out to be +16/3 here. The value of X will come out to be +4/3 here. Now, let's calculate the oxidation state of this particular iron here. This particular iron. Let the oxidation state of this iron is X. Right? How many iron atoms? It is 0.93. Oxygen will show -2 oxidation state. Net charge is 0. When you solve the X, X value will come out to be +200 divided by 93. +200 divided by 93. Right? So this is how you calculate oxidation states of different elements in a compound. As simple as that. Right? Now, my dear students, there are a few more things. If I talk about this NH4NO2, remember this NH4NO2 exists in the form of NH4 positive dot NO2 negative. NH4 positive dot NO2 negative. The oxidation state of this nitrogen is calculated separately. The oxidation state of this nitrogen is also calculated separately. And let me tell you, the oxidation state of this nitrogen comes out to be -3. And the oxidation state of this nitrogen comes out to be +3. Right? You have to consider this as a separate entity and calculate the oxidation state of nitrogen. You have to consider this also as the separate entity and calculate the oxidation state of nitrogen. So one nitrogen is in -3 and another nitrogen is going to be in +3 oxidation state. Okay? As simple as that. Am I clear to everyone? Quickly, let me know in the chats. One more important thing, guys. Remember, the maximum oxidation state of an element. The maximum oxidation state of an element can never be greater than +7. The maximum oxidation state of an element can never be greater than +7. Except in case of osmium tetroxide, OSO4, where the oxidation state of osmium is equal to +8. Where the oxidation state of osmium is equal to +8. So remember this particular point as well. The maximum oxidation state of an element, it can never be greater than +7. There is one exception which you have to remember, right? That is osmium. Osmium in osmium tetroxide, it shows what? Osmium in osmium tetroxide shows +8 oxidation state. Remember this particular point as well. Okay. Now, my dear students, if I take a compound CrO5, if I ask you what is the oxidation state of this chromium, you'll assume the oxidation state of chromium to be X. Oxygen shows -2. There are 5 oxygen atoms. Net charge is 0. So by means of this, the value of X can come out to be +10. But is +10 possible? +10 is not possible. The maximum oxidation state of an element, can never be greater than +7, right? Except osmium in case of osmium tetroxide. Perfect. So I think there is some mistake which we are doing here. Now it is the time to rectify that mistake with the help of structure of CrO5. So you need to mark your heading as structures of different compounds. Structures of some important compounds, I must say. There are some structures of important compounds which I want every one of you to remember. Because from these structures, questions have been many a times asked and will be asked too. Okay? Will be asked too. The first is your CrO5. Remember its structure. CrO5, let me tell you, it has got a butterfly structure. It has got a butterfly type structure. Remember the CrO5, it is deep blue in color. So first of all, CrO5. Let this be chromium. This is double bonded oxygen. Oxygen, single bond. Similarly, oxygen, single bond. Now from the structure, you can easily get the oxidation state of chromium. How exactly? Have a look. There is a double bond here between chromium and oxygen. Now among chromium and oxygen, which one is more electronegative? I would say oxygen. So both these electron pairs will be shifted towards oxygen, due to which oxygen gets -2 and chromium gets +2. Due to this single bond, oxygen gets -1, chromium gets +1. Due to this single bond, -1 +1. Due to this single bond, -1 +1. Due to this single bond, -1 +1. So what is the total charge on chromium here? +2, +3, +4, +5, +6. So remember, +6 is the actual oxidation state of chromium in case of CrO5. It is not +10, it is +6. Okay. This was your structure number 1. Structure number 2, that is CrO6. How the CrO6 looks like? This is how your CrO6 looks like. And when you calculate its oxidation state from the structure, it comes out to be +6. Right? It comes out to be +6. Okay. You have to remember all the structures with whatever I'll be giving you guys. Right? The next one is what you call as Carrot's acid. Carrot's acid, whose formula is H2SO5. My dear students, in case of H2SO5, S double bond O, oxygen attached with hydrogen. This is oxygen, and hydrogen. This is the structure of your H2SO5. Now, if you look carefully, have a look on this particular double bond between oxygen and sulfur. Oxygen is more electronegative, so -2 +2. Due to this double bond, oxygen -2, this +2. Due to this single bond, sulfur +1. Due to this single bond, sulfur +1. So what is the total charge on sulfur? +2, +4, +5, +6. So the oxidation state of sulfur, remember in case of H2SO5, is your +6. Right? This was your Carrot's acid, H2SO5. Then comes, my dear students, there is one more compound which is what you call as oleum. What is the formula for oleum? It is H2S2O7. How this oleum looks like? This is SOS, double bond O, oxygen attached with hydrogen. This is double bond O, oxygen attached with hydrogen. Now, if you look carefully, this particular sulfur, double bond O. So due to this double bond, sulfur carries +2. Due to this double bond, sulfur carries +2. Due to this single bond, sulfur carries +1. Due to this single bond, sulfur carries +1. So this sulfur is right here in +6 oxidation state. Same goes for this sulfur. This sulfur is also in +6 oxidation state. Now, since there are 2 sulfur atoms, if I want to calculate average oxidation state of sulfur, the first sulfur is in +6, second sulfur is in +6. There are total 2 sulfur atoms. So the average oxidation state of sulfur also comes out to be +6. Okay. Average oxidation state of sulfur also comes out to be +6. This was your oleum. Then comes your Marshall's acid. What is the formula for Marshall's acid? Marshall's acid means H2S2O8. H2S2O8. How it exactly looks like? This is S, oxygen, sulfur, double bond O, oxygen with hydrogen. This is double bond O, oxygen attached with hydrogen. Now, my dear students, due to this double bond, sulfur gets +2. Due to this double bond, sulfur gets +2. Due to this single bond, sulfur gets +1. Due to this single bond, sulfur gets +1. So I will say this sulfur is in +6, and eventually this sulfur also is going to be in +6. So average oxidation state of sulfur here will be first sulfur is in +6, second sulfur +6, total 2 sulfur atoms. So the average oxidation state of sulfur here is again going to be +6 only. It is going to be +6 only. So this was your Marshall's acid. My dear students, then you have got one more compound, that is K3CrO8. K3CrO8. How exactly it looks like? How exactly it looks like? See, this is chromium, oxygen, oxygen, single bond. This is oxygen, oxygen. This is oxygen, oxygen. Similarly, this oxygen, oxygen attached with potassium, potassium, and potassium. This is the rough structure of your K3CrO8. Now, first of all, if I ask you, what is the oxidation state of this chromium? See, due to this single bond, chromium gets +1. Due to this single bond, chromium +1. This single bond, +1. Due to this single bond, +1. Due to this single bond, +1. So +1, +2, +3, +4, +5. So oxidation state of chromium here is just going to be +5, right? It's just going to be +5. I believe it's clear. Yeah? I believe it's clear to everyone, right? So this was your K3CrO8. Now, my dear students, there is one more compound, that is Na2S4O6. Na2S4O6. Remember its structure as well, right? This is important. Questions have been asked from this particular compound in your JEE examination. This is your Na2S4O6. Its rough structure. Due to this double bond, sulfur gets +2. Due to this double bond, sulfur gets +2. Due to this single bond, sulfur gets +1, right? Similarly, this sulfur, on one side is sulfur, another side is sulfur, so nothing. This sulfur, due to the double bond, +2. Due to the double bond, +2. Due to the single bond, +1. Now get the oxidation state of all the sulfur atoms. This sulfur is in +5. This sulfur is in 0. This sulfur also in 0. This sulfur in +5. My dear students, if I want to calculate average oxidation state of sulfur, the first sulfur is in +5 oxidation state, second one 0, third one 0, fourth one +5, divided by total 4 sulfur atoms. So the average oxidation state of sulfur here in this compound will be +2.5. It will be +2.5. This was your Na2S4O6. Now similarly, my dear students, we have got CaOCl2, your bleaching powder. CaOCl2, your bleaching powder. Yeah, CaOCl2. How it looks like? I'll make its rough structure. This is its rough structure. Now, my dear students, look carefully. If you talk about this bond between oxygen and chlorine, oxygen is more electronegative, so chlorine will get +1. Here, chlorine is more electronegative, so it gets -1. So one of the chlorine is having +1. Second chlorine is having -1. There are 2 chlorine atoms, so the average oxidation state of chlorine in bleaching powder is equal to 0. Right? Average oxidation state of chlorine in bleaching powder is equal to 0. Similarly, there is one more compound which will be asked, BASCN whole twice. BASCN whole twice. Its structure is something like this. BAS C triple bond N. This is S C triple bond N. Now, my dear students, let's try to check the oxidation states of all these elements over here. Try to understand what I'll be saying. Due to this triple bond, nitrogen is more electronegative, so due to this triple bond, -3 +3. Among carbon, sulfur is more electronegative, so -1 +1. Barium, sulfur is more electronegative, -1 +1. Due to this particular bond, again -1 +1. Due to this bond, -1 +1. Due to this triple bond, -3 +3. Now you can calculate oxidation state of each element. Nitrogen here is in -3, carbon will be in +4, sulfur will be in -2, barium will be in +2, sulfur here -2, carbon here +4, and nitrogen here -3. Okay. Similarly, there are a few more compounds which you need to know. For example, if I talk about Br3O8, how it exactly looks like? This is bromine, and bromine, double bond O, double bond O, double bond O. Similarly, double bonded oxygen, double bond oxygen, double bond oxygen. This is double bond O, this also double bond O. Now, my dear students, have a look. Due to this double bond, bromine gets +2. Due to this double bond, bromine gets +2. Due to this double bond, bromine gets +2. So this bromine is in +6 oxidation state. Similarly, this bromine will be in +4 oxidation state, and this bromine also is going to be in +6 oxidation state. So if I want to calculate average oxidation state of bromine, it's going to be +6, +4, +6 divided by 3 bromine. So 6, 6, 12, 4, 16. So it's going to be plus 16 by 3. So average oxidation state of bromine in Br3O8 is going to be how much? It's going to be plus 16 divided by 3. Similarly, you have got C3O2. You have got C3O2. This is carbon, double bond carbon, double bond carbon, double bonded oxygen, double bonded oxygen. My dear students, due to this double bond, carbon will show plus 2. Due to this double bond, carbon will show plus 2. And this carbon will show 0 oxidation state because on one side carbon, on another side also carbon. If I want to calculate average oxidation state of carbon, the first carbon is in plus 2, second 0, third plus 2. There are 3 carbon atoms. So the average oxidation state of carbon here is going to be plus 4 by 3. Plus 4 by 3. I hope this is also clear to everyone. I hope this is also clear to everyone. Right? Am I clear till here? Am I clear till here? There are a few more structures which I would want you guys to remember. What all structures? First one is H3PO2. Then you have got H3PO3. Then you have got H3PO4. And then you have got H3PO5. These are some structures. I mean, these are some compounds whose structures you are supposed to know. What exactly you are supposed to do? First of all, put a double bond between phosphorus and oxygen everywhere. Put a double bond between phosphorus and oxygen everywhere. Okay. Now, my dear students, we had 2 oxygen, out of which 1 is utilized. So 1 is still there. Give 1 hydrogen to this, 1 to this, and 1 to this. This is your structure of H3PO2. Similarly, H3PO3. H3PO3. Give 1 hydrogen directly to phosphorus. So H3PO3. H3PO4. This is the structure of your H3PO4. H3PO5. Oxygen, hydrogen. Oxygen, hydrogen. This is oxygen, oxygen with it hydrogen. Okay, with it hydrogen. I hope this is clear to everyone. If you got to know about these structures, you can easily calculate the oxidation state of this particular phosphorus. And let me tell you, this phosphorus will be in plus 1 oxidation state. This phosphorus is in plus 3 oxidation state. This phosphorus will be in plus 5 oxidation state. And this phosphorus also will be in plus 5 oxidation state. Am I clear? Am I clear, people? You have to remember these structures. You have to remember these structures. Okay? You have to remember these structures, people. These are very, very, very important. These are very, very, very important. These are very important. Now, people, after getting to know about the structures and the oxidation states of different elements through structures, now what is the next thing which we are supposed to do? We should know, first of all, what is oxidation and what is reduction. We should first of all know what is oxidation and what is reduction. Just remember one thing. Whenever in a reaction you see an element undergoing increase in its oxidation state. Whenever oxidation state of an element increases during the reaction. Whenever oxidation state of an element increases during the reaction, remember that element would be undergoing oxidation. And remember, the one that undergoes oxidation, that's what you call as reducing agent. That's what you call as reducing agent. Okay. Similarly, remember, decrease in the oxidation state of an element is something which you call as reduction. And the one that undergoes reduction is something which you call as your oxidizing agent. Which is what you call as your oxidizing agent. For example, people, for example, I'm writing a reaction. The reaction is zinc plus copper dye positive. It gives zinc dye positive plus copper. This is your reaction. So first of all, if I ask you what is the oxidation state of zinc, 0. Oxidation state of copper, plus 2. Oxidation state of this zinc, plus 2. Oxidation state of copper, 0. So zinc is going from 0 to plus 2. 0 to plus 2 means increase. Increase in the oxidation state is what you call as oxidation. So I would say zinc is undergoing oxidation here. The one that undergoes oxidation is going to be your reducing agent. Is going to be your reducing agent, right? Similarly, plus 2 to 0. Plus 2 to 0 means decrease in the oxidation state. Decrease in the oxidation state is what you call as reduction. The one that undergoes reduction is going to be your oxidizing agent. Okay? Right? As simple as that. As simple as that. For example, if I write a general reaction like this, H2 plus 2 times Ag positive, it gives 2 times H positive plus 2 times Ag solid. Let's say this is the reaction. I need to identify my oxidizing agent and reducing agent. How do I exactly identify it? Again, it's pretty much simple. Hydrogen here is in zero oxidation state. Silver is in +1. Hydrogen is a +1. Silver here is in 0. So 0 to +1. 0 to +1 means increase. 0 to +1 means increase. Increase in the oxidation state is what you call as oxidation. So this hydrogen is undergoing oxidation. The one that undergoes oxidation is the reducing agent. +1 to 0. Decrease in the oxidation state. Decrease in the oxidation state is something which you call as reduction. The one that undergoes reduction will be your oxidizing agent. So this is how, my dear students, you are going to identify in a reaction which one is your oxidizing agent and which one is your reducing agent. I hope this is clear to everyone. Let me know once in the chats if this is clear. If you can identify your oxidizing and reducing agent from now onwards, let me know in the chats quick. Let me know in the chats quick. Yeah? Perfect. Quickly. Quickly we will. Guys, is there any spammer in the chats? Can you tell me in the chats? Is there any spammer? Just name it. Just name it. Name it, name it. Doctor something. Doctor something is gone. More. More, quick. More, quick. All right. Listen to something now. This is important. Listen to something. This is important. All right, guys. Try to understand one more thing. Remember, when it comes to your P block elements, they show a range of oxidation state. They show a range of oxidation states. Your P block elements, they show a range of oxidation states. Oxidation states of P block elements, it lies between group number minus 18 to group number minus 10. Group number minus 10. For example, if I talk about chlorine, chlorine is a p block element. Which group it belongs to? It belongs to group 17. So what range of oxidation state chlorine shows? Group number minus 18. So 17 minus 18 comes out to be minus 1. 17 minus 10 comes out to be plus 7. So this is the range of the oxidation states which chlorine can show. Right? For example, talk about oxygen. Oxygen is again a p block element. Which group it belongs to? Group 16. So what range of oxidation states it can show? 16 minus 18 is minus 2 till 16 minus 10 is plus 6. For example, I talk about nitrogen or phosphorus. I talk about phosphorus. Phosphorus belongs to group 15. Phosphorus belongs to group 15. And if you talk about group 15, the oxidation states of group 15 is going to be 15 minus 18 is minus 3. 15 minus 10 is plus 5. So this is the range of the oxidation states which the p block elements show. Now, why do I need this? Why do I need this? For example, if I write a compound here, H3PO4, I have to check whether this substance is the oxidizing agent or reducing agent. I have to check whether this substance is the oxidizing agent or reducing agent. First of all, what is the oxidation state of phosphorus here? It is plus 5. Oxidation state of phosphorus is plus 5. Is plus 5 the maximum oxidation state of phosphorus? Yes. Plus 5 is the maximum oxidation state of phosphorus. So I would say this phosphorus is right now present in its maximum oxidation state. If phosphorus is present in its maximum oxidation state, I would say it cannot further increase its oxidation state. It cannot further increase its oxidation state. If it cannot increase its oxidation state, it cannot undergo oxidation. If it cannot undergo oxidation, it cannot be the reducing agent. So if it is not the reducing agent, that means it is the oxidizing agent. That means it is the oxidizing agent, right? That means it is the oxidizing agent. Let me give you one more example. Let's say we have got, for example, H2S. H2S. You have to check whether it is the oxidizing agent or reducing agent. First of all, sulfur belongs to group 16. Sulfur belongs to group 16. And group 16 shows minimum minus 2, maximum plus 6. Here sulfur, if you check, it is a minus 2. And minus 2 is the minimum oxidation state of sulfur. So I would say sulfur here is already in minimum oxidation state. If sulfur is in minimum oxidation state, that means it cannot further decrease its oxidation state. If it cannot decrease its oxidation state, it cannot undergo reduction. It cannot undergo reduction. If it cannot undergo reduction, it cannot be the oxidizing agent. If it is not the oxidizing agent, that means it's going to be the reducing agent. As simple as that. As simple as that. I believe this is clear. Right? So this is how, my dear students, you check whether the given substance is your oxidizing agent or reducing agent. Okay? Now, people, we are going to enter into one more part of this chapter. That is the most important part of the chapter. Okay? And a lot of students, they find that part tough. What is that exactly? That is concept of equivalent mass. This is something which is super important. Okay? This is something which is super important. Have a look, guys. How do we exactly define the equivalent mass? Let me tell you, equivalent mass is defined as that mass of the substance which can combine or displace either 1 gram of hydrogen or 8 grams of oxygen or 35.5 grams of chlorine or 108 grams of silver or 80 grams of bromine or 80 grams of bromine. That mass of the substance which can combine or displace either 1 gram hydrogen or 8 gram oxygen or 35.5 grams of chlorine or 108 grams of silver, right? What it means exactly. Try to understand what do I say. Try to understand what do I say here. My dear students, for example, I'm writing a reaction like this. N2 plus 3 times H2. It gives what? It gives 2 times NH3. It gives 2 times NH3. Okay. First of all, what is the mass of 3 moles of H2? The mass of 3 moles of H2 is 6 grams. So I'll write 6 grams of hydrogen has combined with. What is the mass of 1 mole of N2? The mass of 1 mole of N2 is 28 grams. So first of all, can I say as per the stoichiometry, can I say 6 grams of hydrogen combines with 28 grams of nitrogen? 6 grams of hydrogen combines with 28 grams of nitrogen. If 6 grams of hydrogen combines with 28 grams of nitrogen, can I say 1 gram of hydrogen combines with 28 divided by 6? The value comes out to be 14 by 3 grams of nitrogen. 14 by 3 grams of nitrogen. What is this particular term? Can I say this is the mass of nitrogen? This is the mass of nitrogen that has combined with 1 gram hydrogen. And that mass of substance which can combine with 1 gram of hydrogen, what do I call that as? I call that as the equivalent mass. So this 14 by 3 is nothing but it is the equivalent mass of nitrogen here. This is the equivalent mass of nitrogen. This is that mass of nitrogen which has combined with 1 gram hydrogen. And that mass of substance which can combine either with 1 gram of hydrogen or 8 grams of oxygen or 35.5 grams of chlorine, what do we call that as? We call that as the equivalent mass of the substance. I believe this is clear. For example, you have got the reaction like this. Mg plus O2. Mg plus O2 makes it MgO. You should know it, right? Let's try to balance the reaction. This is 2 times. This is 2 times. The reaction is balanced. For example, I want to calculate the equivalent mass of magnesium. And as you can see, magnesium is combining with O2. Magnesium is combining with oxygen. So I will have to calculate that mass of magnesium. I will have to calculate that mass of magnesium which combines with 8 grams of oxygen. As per definition, I have to check that mass of magnesium which combines with 8 grams of oxygen. So that's something which I have to check. How do I check that? Try to understand. What is the mass of 1 mole of O2? Mass of 1 mole of O2 is 32 grams. So I'll write simply 32 grams of oxygen combines with. What is the mass of 2 moles of magnesium? The mass of 2 moles of magnesium is 48 grams. The mass of 2 moles of magnesium is 48 grams. I will say 32 grams of oxygen combines with 48 grams of magnesium. 32 grams of oxygen combines with 48 grams of magnesium. Therefore, 1 gram of oxygen combines with 48 divided by 32 grams of magnesium. So eventually I can say 8 grams of oxygen. 8 grams of oxygen combines with 48 divided by 32 multiplied by 8. The value comes out to be 12 grams of magnesium. So what is this particular term? If you see carefully, I'll say this is the mass of magnesium. I'll say this is the mass of magnesium that has combined with 8 grams of oxygen. And that mass of the substance which combines with 8 grams of oxygen, what do I call that as? I call that as the equivalent mass of substance. So equivalent mass of magnesium came out to be how much? 12 grams. Am I clear? Am I clear, people? Now, remember one thing. There is one simple formula with the help of which we can calculate equivalent mass of the substance. Equivalent mass of the substance is nothing but it is molar mass of the substance divided by the n factor of substance. Equivalent mass of the substance is nothing but it is molar mass of the substance divided by n factor of the substance. N factor is also called as valency factor. N factor is also called as valency factor. Now, my dear students, how do we get the n factor of different substances? How do we get n factor of different substances? Okay? How do we get n factor of different substances? That's important. Remember it. So first of all, let's talk about the n factor of elements. N factor for elements. N factor of element is nothing but valency of an element. N factor of an element is nothing but valency of an element. For example, talk about nitrogen. Okay, talk about nitrogen, talk about oxygen, talk about magnesium, talk about sodium. These are different elements which I've taken. If I ask you what is the valency of this nitrogen, 3, valency of oxygen, 2, valency of this magnesium, 2, valency of this sodium, 1. Whatever is going to be the valency of an element, that is something which you call as n factor of an element. And once you get n factor of an element, you can easily calculate equivalent mass. So I'll say equivalent mass of nitrogen is molar mass of nitrogen divided by its n factor. Equivalent mass of oxygen is molar mass of oxygen divided by its n factor. Equivalent mass of magnesium is molar mass of magnesium divided by its n factor. Similarly, equivalent mass of sodium is equal to molar mass of sodium divided by its n factor. So the first thing which is to be remembered from now onwards, what is that? What is that? N factor of the elements is nothing but valency of the element, right? This is the first n factor which you have to remember. Number 2. Number 2 is basically the n factor of salt. N factor of what? N factor of salt. Let me tell you, n factor of salt is nothing but it is LCM of charge on cation, LCM of charge on cation, comma, the charge on anion. LCM of charge on cation, comma, the charge on anion. What does that mean? Let's have a look. For example, I have got NaCl. Okay, I've got NaCl here. For example, I have got MgCl2. Let's say I've got AlCl3. Okay, let's say I've got Al2SO4 whole thrice. Okay, Al2SO4 whole thrice. Try to understand, guys. This is Na1Cl1. Take this one as a charge here. Take this one as a charge here. Take this 2 as a charge here. Take this one as a charge here. Take this 3 as a charge here. Take this one as a charge here. Take this 3 as a charge here. Take this 2 as a charge here. Now, first of all, what is the LCM of 1 and 1? That comes out to be 1. What is the LCM of 2 and 1? That is 2. What is the LCM of 3 and 1? That is 3. What is the LCM of 3 and 2? That is 6. LCM of charge on cation and anion. LCM of charge on cation and anion. What does that give me? That gives me the n factor. And if you got the n factors, you can easily calculate their equivalent masses. How? Their molar masses divided by their n factors. Their molar masses divided by their n factors. Molar masses divided by their n factors. Okay. My dear students, the third category, which is very important, remember that. Third category. That is n factor of acids. N factor of acids. N factor of acid is nothing but the basicity of the acid. N factor of acid is nothing but the basicity of the acid. And how do you define the basicity? Simple words. Number of H positives and acid donates. Number of H positives and acid donates. Or I can say number of OH negatives and acid accepts. Number of OH negatives and acid accepts. Okay. For example, let's say I've got HCl, I've got H2SO4, I've got HNO3, I've got H3PO4. These are different acids which I've taken. If I introduce this acid in water, how many H positives it's going to give me? 1 H positive. How many H positives this is going to give me? 2 H positives. How many H positives this is going to give me? 1 H positive. How many H positives this is going to give me? 3 H positives. And the number of H positives, and acid donates, that defines its n factor. So what is the n factor of HCl? That's 1. What is the n factor of H2SO4? That's 2. What is the n factor of HNO3? That's 1. What is the n factor of H3PO4? That is 3. And if you got their n factors, you can easily calculate their equivalent masses. How? Molar masses divided by their respective n factors. Right? You'll be getting equivalent masses of these acids. Okay? Now, my dear students, one more thing. Remember, an acid donates only that hydrogen. An acid donates only that hydrogen which is attached to what? Which is attached to more electronegative element like chlorine, oxygen, or nitrogen. An acid is going to donate only that hydrogen in the form of H positive, which is attached to more electronegative element like fluorine, oxygen, or nitrogen. What does that mean? Say, look at these acids: H3PO2, H3PO3, H3PO4, H3PO5. I'm asking you to calculate their N factors. Okay. Normally, what do you see? You see 3 hydrogens, so you'll write N factor 3. N factor 3, 3, 3. But that's not the case. Because if you look at the structure of H3PO2, in case of H3PO2, there is only one hydrogen which is attached to more electronegative element like oxygen. And an acid donates only that hydrogen which is attached to more electronegative element like fluorine, oxygen, nitrogen. Right? So basically, this acid is going to donate only one H positive. This one is going to donate only 2 H positives. This one will donate all the 3 H positives. Even this one will donate all the 3 H positives. And the number of H positives an acid donates, that defines its N factor. So N factor of H3PO2 is 1. N factor of H3PO3 is 2. N factor of H3PO4 is 3. N factor of H3PO5 is also 3. Right? Similarly, one more case I'm showing you. I hope you would have heard about boric acid, BOH whole thrice. When you introduce boric acid in water, what does it form? It forms BOH4 negative. BOH4 negative plus H positive. First of all, this boric acid, it's a weak Lewis acid. This boric acid is a weak Lewis acid. Remember it. How many OHs do you see here? 3. Now, how many OHs do you see here? 4. It had 3 OHs. Now it has 4. When it is introduced in water, now it has 4 OHs. So basically, can I say this boric acid is accepting one OH negative? And the number of OH negatives an acid accepts, that defines its N factor. So remember, if you talk about boric acid, its N factor is 1. Because it is in water, it's accepting one OH negative from water. It is accepting one OH negative from water. And the number of OH negatives an acid accepts, that also defines its N factor. That also defines its N factor. Am I clear with this? Am I clear with this, people? Say it once in the chats. Say it once in the chats, everyone. Perfect. I hope this is clear. Now, my dear students, one more thing. One more thing. For example, I'm writing a reaction like this. H2SO4 plus NaOH. Okay, let's say it gives NaHSO4. With this you have water. This is one of the reaction which I have written. The second reaction I'm writing, H2SO4 plus 2 times NaOH. It gives Na2SO4 and you have got 2 times water. 2 times water. I want you to calculate N factor of H2SO4 in both these reactions. I want you to calculate N factor of H2SO4 in both these reactions. See guys, here you have got 2 hydrogens and here you have got 1 hydrogen. 2 hydrogens, 1 hydrogen. What does that mean? That means this H2SO4, it has lost 1 H positive. And the number of H positives an acid loses, that defines its N factor. So N factor of H2SO4 in this reaction, you can remember it like this as 1. Okay. Similarly, you have got 2 hydrogens here. Here you have got no hydrogen. So this H2SO4 has lost both these hydrogens in the form of H positives. So its N factor here is 2. Okay. Its N factor here is 2. Perfect. You can remember it like this. Same goes for, my dear students, same goes for N factor of bases. Same goes for N factor for bases. N factor of bases is nothing but it is the acidity of the base. Acidity of the base. And how do you define the acidity? Number of OH negatives are base donates, number of OH negatives are base donates, or I can say number of H positives a base accepts. A base accepts. Okay. Number of OH negatives a base donates, number of H positives a base accepts. Okay. For example, have a look. Let me take some common bases. NaOH. Okay. NaOH you have got potassium hydroxide. You have got barium hydroxide. BaOH whole twice. You have got calcium hydroxide. When you introduce them in water, this is going to give us one OH negative. This is going to give us one OH negative. This is going to give us two OH negatives. This is also going to give us two OH negatives. And the number of OH negatives, are base donates. Number of OH negatives are base donates. That defines its n factor. So n factor of this base is 1. N factor of this base is 1. N factor of this base is 2. Even n factor of this base is 2. Right? If you got the n factors, you can calculate their equivalent masses. How exactly? Their molar masses divided by their n factors. Now, my dear students, you must have heard about NH3. NH3 is also a base. When you introduce this in water, it gets converted into NH4 positive. It gets converted into NH4 positive. See, this NH3 had 3 hydrogens here. Now, it got converted into NH4 positive, where you have got 4 hydrogens here. So, basically, this NH3, when we introduce this in water, this NH3 is accepting one H positive. It is accepting one H positive. And the number of H positives a base accepts, that also defines its n factor. So, n factor of NH3 here is just going to be 1. Okay, it is just going to be 1. I hope I'm clear to everyone. Okay, perfect. Is it clear? Is it clear, people? Say it once in the chats. Say it once in the chats. Yeah? Even I'm thinking to break this session into 2 parts. Okay? I think this will be the last chapter which we'll be doing for today. And it's not going to take more than 1 hour. Okay? All right? Better is going to be, I'll take it in 2 parts. Don't worry. Don't worry. Let's complete this chapter first, then we'll talk about it, okay? Let's complete this chapter first, then we'll talk about it. All right? See, guys. This was n factor of bases. Now, my dear students, how do we calculate n factors of oxidizing agents and reducing agents? Remember this as well. N factors of oxidizing and reducing agents. How do we get it? Let me tell you, n factor of oxidizing reducing agents is always equal to number of moles of electrons, lost, gained, or exchanged. Lost, gained, or exchanged by 1 mole substance. Number of moles of electrons lost, gained, or exchanged by 1 mole substance. What does it mean? What does it mean? How do we calculate it? Try to understand. For example, I've got the reaction like this. A2 plus B2. Let's say it gives 2 times A positive plus 2 times B negative. Okay? 2 times A positive plus 2 times B negative. Its oxidation state here is 0, here is 0. And the oxidation state of A is +1. Oxidation state of B is -1. Now see, 0 to +1 means increase in the oxidation state. Increase in the oxidation state is what you call as oxidation. The one that undergoes oxidation is the reducing agent. If A2 is the reducing agent, this B2 is the oxidizing agent. Okay. Now the point is, how do I calculate n factor of this A2? How do I calculate n factor of this A2? And how do I calculate n factor of this B2? How do you do it? First of all, take the modulus. Modulus of change in the oxidation state of A. Oxidation state of A is changing from 0 to +1. Oxidation state of A is changing from 0 to +1. Now calculate the change in oxidation state, which is final oxidation state of A minus final oxidation state of A minus the initial oxidation state. The value comes out to be 1. 1 is the change in the oxidation state for one atom of A. But here I've got 2. So I'm multiplying this with 2. The value comes out to be 2. So 2 is going to be the n factor of A2 in this reaction. 2 is going to be the n factor of A2 in the reaction. N factor of B2. N factor of B2. Calculate the change in oxidation state. 0 to -1. 0 to -1. Calculate the change. Final oxidation state minus initial oxidation state. The value comes out to be 1. 1 is the change in the oxidation state for one atom of B. How many we have? 2. So 1 multiplied by 2 comes out to be 2. This is the n factor of B2 in the reaction. This is the n factor of B2 in the reaction. Yeah? Okay? Yeah? So this is how you calculate the n factors of oxidizing agents and reducing agents. This is how you calculate n factors of oxidizing agents and reducing agents. Now, my dear students, we have got two important oxidizing agents which you have to remember. One is going to be your KMnO4 and one is going to be your K2Cr2O7. These are two strong oxidizing agents. These are two very, very, very strong oxidizing agents. Okay, these are two very, very, very strong oxidizing agents. Let me first of all tell you, this KMnO4, in acidic medium, it gets converted into Mn dipositive. I'm talking about acidic medium. In acidic medium, it gets converted into Mn dipositive. My dear students, in neutral or slightly alkaline medium, in neutral or slightly alkaline medium, it gets converted into MnO2. And in strongly alkaline medium, it gets converted into MnO4 dinegative. You have to remember this first of all. This KMnO4, in acidic medium, it gets converted to Mn dipositive. In neutral medium, MnO2. In strong alkaline medium, MnO4 dinegative. Now, how do I get the n factors of KMnO4 in all these mediums? How do I get n factor of KMnO4 in all these mediums? See, first of all, oxidation state of manganese here is +7. Here it is +2. +7 to +2 changes 5. So n factor of KMnO4 in acidic medium is 5. +7 to +4. +7 to +4 changes 3. So n factor of KMnO4 in neutral medium is 3. +7 to +6 changes 1. Right? So n factor of KMnO4 in strongly alkaline medium is 1. So you have to remember these three things. 5, 3, 1. N factor of KMnO4 in acidic medium 5. Here it is 3. Here it's 1. Now this K2Cr2O7, only remember one thing. In acidic medium, it gets converted into Cr tripositive. In acidic medium, it gets converted into Cr tripositive. Here its oxidation state is +6. Here it is +3. +6 to +3, what is the change? Change is 3. 3 is the change for one chromium. I have 2. So 3 2s comes out to be 6. So remember, n factor of K2Cr2O7 in acidic medium is going to be 6. So this is how you calculate the n factors as well. Okay, this is how you calculate the n factors of these two oxidizing agents as well. right? I hope this is clear. Now, my dear students, one more thing. There are some very, very, very important reactions. Some important reactions of KMnO4 and K2Cr2O7. Some important reactions of KMnO4 and K2Cr2O7. In which medium? In acidic medium. In acidic medium. Some important reactions of KMnO4 and K2Cr2O7 in acidic medium. Remember what I say. Okay? Remember what I say. My dear students, the first one. KMnO4 as well as K2Cr2O7 converts Fe di positive to Fe tri positive. In which medium? In acidic medium. KMnO4 as well as K2Cr2O7. KMnO4 as well as K2Cr2O7. It converts Fe di positive into Fe tri positive. It converts Fe di positive into Fe tri positive. Okay. If you want to write the reactions, you can write the reactions too. First reaction. KMnO4 converts Fe di positive. In which medium? Acidic medium. Into what? Into Fe di positive. And itself KMnO4 in acidic medium gets converted into Mn di positive. And with this you just have to write water. With this you just have to add water. Similarly, K2Cr2O7 does the same thing. Converts Fe di positive. In which medium? In acidic medium. Into what? Into Fe tri positive. Itself gets converted into Cr tri positive. And with this you just have to add water. Right? With this you have to add water. Second one. The same KMnO4 as well as K2Cr2O7 converts Sn di positive to Sn plus 4. Converts Sn di positive to Sn plus 4. Sn di positive to Sn plus 4. So the reactions are going to be KMnO4 converts Sn di positive. In which medium? Acidic medium. Into what? Into Sn plus 4. Itself gets converted into Mn di positive. With this, you are going to write water as well. If I talk about K2Cr2O7, K2Cr2O7 converts Sn di positive. In which medium? Acidic medium. Into what? Sn plus 4. Itself gets converted into Cr tri positive. And with this, you are going to write water as well. Okay? Right? Similarly, my dear students, there are few more reactions, which I'm not going to write the reactions now. I'm going to show you something important. KMnO4 converts I negative into I2 as well. Same goes for K2Cr2O7. I negative into I2 in acidic medium. I believe you can write the reactions on your own, right? It converts H2O2 into O2. KMnO4 as well as K2Cr2O7 in acidic medium converts H2O2 into O2. KMnO4 as well as K2Cr2O7 converts H2S into sulfur. H2S into sulfur. KMnO4 as well as K2Cr2O7 converts oxalate ion into carbon dioxide. KMnO4 as well as K2Cr2O7 converts oxalate ion into what? Into carbon dioxide. In which medium? In acidic medium. I believe you can write the reactions on your own now. Like I wrote reactions here. In the similar way, you guys are going to write the reactions on your own. Am I clear with this? Am I clear with this, guys? Okay, one more. KMnO4 as well as K2Cr2O7 converts SO2 into SO4 dinegative. SO2 into SO4 dinegative. Okay? Got it? Got it, people? Is it clear? Say it quick. Say it quick. Right? Equation of third. Equation of third is pretty much simple. KMnO4 converts I negative in acidic medium into I2. Itself gets converted into Mn di positive with this water. Same goes for K2Cr2O7. K2Cr2O7 converts I negative in acidic medium into I2 itself gets converted to Cr positive with this water. Okay? I hope this is clear. I hope this is clear. I hope this is clear. All right, guys? All right? Is it clear to everyone? One last topic and we are done. One last topic and we are done. One last topic and we are done. But this is also important to have an eye on this particular topic as well. Okay? And after this, we'll be left with only two chapters. One is thermo and one is equilibrium, right? We'll do that in part 2 only. Because right now, if we start thermo equilibrium, I don't want to go in hurry for that. Okay? So my dear students, how do you balance the reactions? How do you balance the redox reactions? How do you balance the redox reactions? How do you balance the redox reaction? Basically, there are many methods: oxidation number method, ion electron method. But for your NEET examination, you are not supposed to remember all the methods. You just remember one method, and from that, you just balance the reaction. You just balance the reaction. How exactly? Let me show it to you. First of all, whenever a question comes related to balancing, I prefer balancing the reaction with the help of oxidation number method. I prefer to balance the reaction with the help of which method? Oxidation number method. So first of all, we'll do the oxidation number method in acidic medium. First of all, we'll do the oxidation number method. In which medium? In acidic medium. We'll do the oxidation number method in acidic medium. Right? Okay. Now guys, have a look. Someone is saying, sir, why you teach half in one series, half in another series? What do you mean? What do you mean? We are just left with one more marathon and we are done with chemistry syllabus. So what have I left? Try to acknowledge what you are getting. That too free of cost. Okay? Try to acknowledge. Yeah? Go to the Game of NEET series. Go to this playlist. Completed. What have I left? Now they won't comment. Yeah? Exactly. All right, have a look, people. Have a look. We are going to do the balancing of redox reactions with the help of which method? Oxidation number method. In which medium? Acidic medium. In acidic medium. Have a look, guys. For example, I've got the reaction like this. MnO4 negative plus Fe di positive. It gives Mn di positive plus Fe tri positive. Let's say I have to balance this reaction in acidic medium. Let's say I have to balance this particular reaction in acidic medium. Now, first of all, how do I balance it? How do I balance it? Just understand what I'll be doing. My dear students, first of all, I'm going to write the sequence of the things here, which you have to follow while balancing. First of all, get the n factors of reactants. Get the n factors of reactants, number one. Okay. Number two, crisscross the n factors. Number three, balance all the atoms. Except hydrogen and oxygen. Balance all the atoms except hydrogen and oxygen. Okay. Now, people, after this, balance oxygen with the help of water. And at the end, balance hydrogen with the help of H positives. See what we are going to do here. Try to understand. Step by step, I'm going to solve the things. What is the oxidation state of manganese? +7. What is the oxidation state of manganese? +2. So +7 to +2. So what will be the n factor of this MnO4 negative? N factor of MnO4 negative is 5. +2 to +3. What is the change? 1. So its n factor is 1. So I think I got the n factors of the reactants. Once you get the n factors of the reactants, you need to crisscross them. Make this 1 as the coefficient here. Make this 5 as the coefficient here. Okay. So I've gotten the n factors first. Then I have crisscrossed these n factors. After crisscrossing these n factors, balance all the atoms except hydrogen, oxygen. See, we have got 1 manganese, we have got 1 manganese. We have got 5 iron, we have got 5 iron. Okay, I have balanced all the atoms except hydrogen, oxygen. After this, I'm going to balance oxygen. See, how many oxygen on this side? 4. How many oxygen on this side? No one. So this side is oxygen deficient. How much oxygen deficiency is on this side? 4 oxygen deficiency. So just add 4 water molecules on this side. Now balance hydrogen. How many hydrogens on this side? No. How many hydrogens on this side? 8. So this side is hydrogen deficient. How much? 8 hydrogen deficiency. So add 8 H positives. The reaction is balanced. The reaction is automatically balanced. Okay? The reaction is automatically balanced. For example, I'm giving you one more reaction. Let's say you've got the reaction like this. MnO4 negative plus Sn di positive gives Sn plus 4 plus Mn di positive. You have to balance this reaction in acidic medium. You have to balance this particular reaction also in which medium? Acidic medium. How do we do it? See, MnO4 negative, its n factor is 5. +2 to +4, its n factor is 2. Crisscross the n factors. Make this 2 as the coefficient here. Make this 5 as the coefficient here. Okay. Once you crisscross the n factors, now you are supposed to balance the atoms except hydrogen, oxygen. Okay. So 2 manganese on this side. This is 2 manganese. 5 tin on this side. This is 5 tin. Okay. Now after balancing all the atoms except hydrogen, oxygen, we need to balance what? We need to balance oxygen. Try to understand. How many oxygen on this side? 8. How many oxygen on this side? None. So this side is oxygen deficient. So add 8 water molecules on this side. How many hydrogens on this side? 16. So add 16 H positives on this side. Now this reaction is automatically balanced. Am I clear? Am I clear, people? Am I clear? Am I clear? Am I clear, everyone? Yeah. So this is how you balance the redox reactions in which medium? In acidic medium. This is how you balance the. See, you're not supposed to balance the charge here. The charge automatically gets balanced in acidic medium. Okay. Now let's have a look on balancing of the reaction in basic medium. Let me take some example here. Let me take some example here in basic medium. Okay. One example and we are done. Okay. One example and we are done. In case of basic medium also, what you have to do? First of all, you will be calculating the n factors of reactants. Once you get n factors of reactants, then you are supposed to crisscross these n factors. Once you crisscross these n factors, balance all the atoms. Balance all the atoms except hydrogen, oxygen. Except hydrogen, oxygen. After that, balance the negative charge with the help of OH negatives. Balance the negative charge with the help of OH negatives. Then balance oxygen with the help of water. Okay? And here you are not supposed to balance hydrogen. Hydrogen automatically gets balanced. For example, tell me first of all, what is the n factor of this Cl2? 0 to minus 1. 0 to minus 1 change is 1. 1 is the change for one atom, I have 2. So its n factor is 2. Iodine plus 5 to plus 7. Plus 5 to plus 7. Change is 2. So its n factor is also 2. So I got the n factors of reactants. I got the n factors of reactants. Now crisscross these n factors. Make this 2 as the coefficient here. Make this 2 as the coefficient here. Okay. So I've crisscrossed the n factors. After crisscrossing the n factors, what is the next thing which we are supposed to do? What is the next thing which we are supposed to do? Balance all the atoms except hydrogen, oxygen. So how many chlorine we have here? 4. So make it 4. How many iodine we have here? 2. So make it 2. Okay. Now after reaching till here, what do I have to do? I have to balance negative charge with the help of OH negatives. Tell me, is there charge on this? No. 1 IO3 carries minus 1 charge. So 2 IO3s will carry minus 2 charge. 1 IO3 carries minus 1. 2 IO3s carries minus 2. 1 Cl carries minus 1. 4 Cl carries minus 4. 1 IO4 carries minus 1. 2 IO4s carries minus 2. So on left side, the charge is minus 2. On right side, the charge is minus 6. On left side, the charge is minus 2. On right side, the charge is minus 6. Right? So which side is negative charge deficient? Left side is negative charge deficient. How much negative charge deficiency is there? There is negative charge deficiency of 4. Right? So just add 4 OH negatives on this side. Because negative charge deficiency is complemented by OH negatives. Okay? Just add 4 OH negatives on this side. The charge is balanced now. The charge is balanced. After balancing the charge, balance oxygen atoms. 4, 3 2s are 6. 6 plus 4, 10. 10 oxygen atoms on this side. 4 2s are 8. 8 oxygen atoms on this side. Which side is oxygen deficient? Right side is oxygen deficient. How much oxygen deficiency is there? 2 oxygen deficiencies there, right? So just do one thing. Add 2 water molecules on that side, which is oxygen deficient. Now you don't have to balance hydrogen. Hydrogen automatically would have got balanced. Okay? Perfect. And with this, your redox is also done, my dear students. Perfect. So tell me, whatever things we discussed, are all the things clear? I'm thinking to take the next session first as complete chemistry revision. Okay. This one, that's not required. Whatever things I've discussed here, this is more than sufficient. Okay, I am thinking to take first one session, which is going to be the complete chemistry revision. But I'll take that after 3 to 4 days. After 3 to 4 days, I'll do that. Well, in class 11th inorganic, there are 2 chapters left. One is thermo and one is equilibrium. I'll come up with that session as well. Don't worry. Don't worry. Okay. So how is your preparation currently going? Is it going well? Tell me one thing. Are you here for the revision? Are you doing the revision or you are studying things? I want to know this. Okay. Majority is studying, huh? Got it, got it, got it. That's great. Twelfth organic will be also done. Don't worry. Oh, sorry, inorganic. Why are you worried? That will be also done. Guys, we have got 17 days left, right? Don't worry. Everything will be taken care of. Everything will be taken care of. Don't worry. All right. Completed formula or concepts based revision. That's great. All right, I'll tell ourselves to complete those 50 concepts. In chemistry, we had completed that, right? In chemistry, we had completed those 50 concepts. See, I think 20 to 30 concepts I took, and HSP sir also took some 20 concepts. Right? In chemistry, we had completed that. Hello guys, I'll take a leave with this. I would need one comment in the comment section once the video ends. That is class 11th physical chemistry part 1 done and dusted. Class 11th physical chemistry part 1 done and dusted. This is something which I would want in the comment section of this particular video. Okay? Chalo. I'll see you guys soon. Till then, you guys take care. Bye-bye. God bless you. Keep studying. Right? Okay? I'll keep on coming with more sessions like this so that your scores in the NEET 2025 will be better.